Space is not quiet. It only seems that way because most of its violence happens on scales far beyond human comprehension. Somewhere out there, hundreds of millions of light years away, a silent explosion once tore through a cluster of galaxies with a force so immense that scientists say it was the largest known release of energy since the Big Bang. No visible flash, just the slow, unstoppable expansion of a cavity in space, larger than our entire Milky Way. For eons, it went unnoticed, its scars buried in the glow of distant X-rays, until human instruments finally caught the faint echo of what happened. Why did it erupt? What triggered such unimaginable violence? And what does it tell us about how energy moves, builds, and explodes across the universe? What exactly is a supercluster? A supercluster is one of the universe's grandest creations. A sprawling web of galaxies stretching hundreds of millions of light years across. It's not a single object, like a star or a galaxy, but a vast collection of galaxy clusters bound loosely together by gravity. If the universe were a cosmic city, a galaxy would be a single home, a galaxy cluster would be a neighborhood, and a supercluster would be an entire nation. It is within these enormous regions that most of the universe's matter and galaxies are found, connected by invisible threads of dark matter and separated by enormous cosmic voids where almost nothing exists. When astronomers first began mapping galaxies on a large scale, they expected to see a fairly random spread, small dots scattered evenly across space. Instead, what they found was structure. Galaxies were not evenly distributed, but formed patterns, clusters, filaments, and walls. By the late 20th century, as technology improved and telescopes began collecting redshift data for thousands of galaxies, a picture emerged of a cosmic web. This web is composed of long filaments of galaxies and gas that weave around immense voids, creating a honeycomb-like pattern on the largest scales. At the intersections of these filaments sit the superclusters, the densest, most complex regions in the universe's large-scale structure. A supercluster contains clusters of galaxies, with each cluster holding hundreds or thousands of galaxies on its own. Between the clusters are smaller groups of galaxies, clouds of intergalactic gas and streams of dark matter that help hold everything together. Despite this, the gravitational bonds between the clusters in a supercluster are relatively weak compared to those inside a single cluster. Over billions of years, the expansion of the universe will slowly pull these clusters apart. This means that while superclusters appear as unified structures today, they're more like temporary gatherings of galaxies rather than permanent cosmic islands. To understand what makes a supercluster, it helps to compare it with a galaxy cluster. A galaxy cluster, like the Virgo cluster or the Coma cluster, is a tightly bound group of galaxies held together by gravity. They are dense, compact, and their galaxies interact frequently. Superclusters, on the other hand, are enormous regions that contain many such clusters. Their size can reach up to 500 million light-years across, or even more. The largest known, the Hercules Corona Borealis Great Wall, stretches across 10 billion light-years, so vast that light takes almost the entire age of the universe to cross it. Yet even this immense structure is not truly bound by gravity as a whole. It's more accurate to think of it as a region of higher density within the overall cosmic web. Astronomers identify superclusters by studying how galaxies are distributed across the sky and by measuring their redshifts, the stretching of their light due to the universe's expansion. By plotting millions of galaxies in three-dimensional space, scientists can see where matter tends to clump together. These clumps and filaments form the outline of superclusters. In modern surveys, such as those from the Sloan Digital Sky Survey, the cosmic web emerges vividly from the data. Patterns of galaxies form enormous arcs and walls with vast empty spaces in between. One of the most famous examples is our own home structure, the Laniakea supercluster, which includes the Milky Way. Laniakea means immense heaven in Hawaiian, and it stretches over 500 million light-years, containing around 100,000 galaxies. Within it lies the Virgo cluster, which itself contains our local group of galaxies, a small cluster that includes the Milky Way and Andromeda. Defining where one supercluster ends and another begins is not simple. Because the universe has no solid borders, astronomers must rely on measurements of motion and density. Galaxies within a supercluster tend to move toward a common gravitational center, creating what is known as a flow. In the case of Laniakea, this flow directs galaxies inward toward the region of the Great Attractor, a massive gravitational anomaly that draws galaxies toward it, including ours. This shared motion helps define the boundaries of Laniakea, separating it from neighboring structures like the Perseus-Pisces supercluster. Superclusters are not evenly shaped or uniform. Some resemble flattened walls, others form long chains, and some are even shaped like knots in a net. These differences arise from how matter collapsed under gravity after the Big Bang. In the early universe, small fluctuations in density created tiny seeds for future structure. Over billions of years, these regions pulled in more matter, forming galaxies and clusters, which then linked together along filaments of dark matter. Superclusters represent the largest scale of this process. They form the skeleton on which galaxies are arranged. If you could strip away the stars and gas and only see dark matter, the superclusters would appear as bright nodes along a cosmic network, giving structure to everything we see. Without them, galaxies would be scattered without any larger order. They also influence how galaxies move and interact. The gravitational pull from massive superclusters can bend the paths of galaxies and even light itself through a phenomenon known as gravitational lensing. This bending helps astronomers map out the distribution of dark matter, since the visible matter alone cannot explain the strength of the observed gravitational effects. Even within a supercluster, there are smaller layers of structure that branch off like roads in a city. Filaments connect clusters across millions of light years, guiding the flow of galaxies toward denser regions. It's along these cosmic highways that galaxies merge, form new stars, and evolve. Superclusters also help scientists test theories about how the universe expanded after the Big Bang. The size, shape, and distribution of superclusters can tell us how matter was spread out in the early universe and how dark energy affects the expansion of space today. If dark energy continues to accelerate that expansion, many of these vast structures will eventually drift apart, leaving isolated islands of galaxies surrounded by growing cosmic emptiness. In the far future, distant superclusters will move beyond the reach of our telescopes, their light stretched so far by the expansion that they will fade into darkness. For much of history, people imagined the cosmos as a relatively small, layered space. Stars in a sky dome, the Milky Way as the edge of existence. Then we learned that the Milky Way is only one galaxy among billions. Now we know even those galaxies form part of a much larger network. A network so vast that the human mind struggles to comprehend its scale. Within the Laniakea supercluster, our Milky Way is just one small ripple in a cosmic sea, drifting toward a gravitational center we can barely locate. And yet, despite their immensity, superclusters are fragile in the grand scheme of things. Gravity binds their clusters only loosely, and the accelerating expansion of the universe will one day pull them apart completely. The galaxies within them will continue their motion, but the connections that define these vast regions will fade. Superclusters are both the largest and most temporary of cosmic structures, snapshots in a universe that is still expanding, still evolving, still reshaping itself on unimaginable scales. The cosmic web and its hidden filaments. The universe, when seen on the largest scales, looks like a web. A vast, intricate network of filaments stretches across space, forming the structure that holds everything together. Within the glowing threads of this web lies almost all the matter that exists, both visible and invisible. In the early days of astronomy, galaxies were thought to be evenly spread throughout space, with a few clusters breaking up the monotony. But as telescopes grew stronger and sky surveys began mapping galaxy positions in 3 dimensions, astronomers noticed long chains of galaxies forming arcs and walls, with enormous voids separating them, empty regions spanning hundreds of millions of light years. these patterns could not be explained by chance alone. Something larger and more organized was shaping the way galaxies arranged themselves. One of the earliest hints of this came in the late 1970s and 1980s, when massive galaxy surveys began tracing out the universe's large-scale structure for the first time. The CFA Redshift survey, conducted by the Harvard-Smithsonian Center for Astrophysics, revealed one of the first striking images of the cosmic web. When plotted, the galaxies formed a wedge-shaped slice of the universe that looked eerily similar to a sponge or a spider's web, with long threads connecting dense nodes of galaxy clusters. The discovery stunned astronomers. For the first time, the universe appeared not as a random sea of galaxies, but as a structured, interconnected whole. These filaments are the true skeleton of the cosmos. They are made mostly of dark matter, the mysterious, invisible substance that makes up about 85% of all matter in the universe. It pulls on visible matter, bends light, and influences how galaxies move. Within these dark filaments, clouds of hydrogen gas and dust gather, providing the material for galaxies to form. The galaxies we observe are therefore like lights decorating the strands of an invisible web. In between these filaments are the voids, enormous, almost empty regions where very few galaxies exist. The contrast between dense filaments and vast voids gives the universe its striking honeycomb appearance when mapped in 3 dimensions. The largest of these voids can stretch hundreds of millions of light-years across, vast cosmic deserts separating the bustling hubs of galaxy activity. The existence of such enormous empty spaces raised questions about how the universe grew to be so uneven. The answer, as cosmologists discovered, lies in the physics of the early universe. Not long after the Big Bang, the universe was nearly uniform, filled with hot plasma that varied only slightly in density. These tiny fluctuations, measured in the cosmic microwave background radiation, acted as seeds for future structure. As the universe expanded and cooled, gravity began pulling matter towards slightly denser regions, amplifying those differences over time. Over billions of years, this process sculpted the universe into its current form. Simulations of cosmic evolution, such as the Millennium Simulation and Illustris, have recreated this process in incredible detail, showing how the first particles of matter slowly gathered into the web-like framework we see today. The cosmic web is not just an arrangement of galaxies, it's an ecosystem. Filaments channel gas toward galaxy clusters, feeding them with fresh material to form new stars. When 2 filaments intersect, their combined gravity creates massive nodes, the locations where superclusters form. These intersections are the crossroads of the universe, where galaxies collide, merge and evolve more rapidly than in quieter regions. Everything that happens on smaller scales, star formation, galaxy evolution, black hole growth, is ultimately influenced by the position of that galaxy within the larger web. Astronomers have found clever ways to study this hidden structure. Because dark matter doesn't emit or absorb light, scientists observe its effects through gravitational lensing. This has revealed the filaments connecting galaxy clusters and superclusters, confirming what simulations had predicted. In 2019, astronomers even managed to directly image a section of one such filament, a 50 million light-year-long bridge of gas connecting 2 galaxy clusters. It was the first visual evidence of the cosmic web's gaseous component, a discovery that transformed theory into reality. Superclusters, such as the Ophiuchus Supercluster, lie along these filaments like massive knots in the cosmic net. The galaxies within it are influenced not just by their local cluster's gravity, but also by the gravitational pull of neighboring superclusters along these invisible threads. The flow of galaxies, gas, and dark matter along these connections creates a dynamic web of movement that stretches across hundreds of millions of light-years. Observing these vast connections is a challenge because most of the web is faint and diffuse. Much of its mass exists as warm, hot intergalactic medium, gas heated to millions of degrees, too faint to see with ordinary telescopes. X-ray and radio observatories, such as Chandra and LOFAR, are helping to detect this hidden matter by tracing its emissions and the way it interacts with cosmic rays. When mapped, these observations reveal long, filamentary bridges between clusters, the arteries of the cosmic web that feed galaxies with matter and shape their evolution over time. Every supercluster, including Ophiuchus, sits within this interconnected framework. No part of the cosmos exists in complete isolation. Even regions separated by hundreds of millions of light-years are linked through the subtle pull of gravity and the faint glow of gas. When astronomers simulate the entire observable universe, they see superclusters connected by these glowing strands, forming a network that extends in every direction. From our perspective, it is almost as if we live inside a vast cosmic organism, with filaments acting as veins and clusters as vital organs. The idea that everything in the universe is connected on such massive scales changes how scientists think about cosmic evolution. Galaxies are not independent actors. The position of a galaxy within the web determines its fate. Those near-dense filaments tend to form stars faster and have more interactions, while those drifting in the quiet voids evolve slowly and in isolation. The web itself acts as both a bridge and a boundary, guiding material where it's needed while leaving other regions barren. As astronomers continue mapping the universe, the cosmic web becomes clearer, but it also grows more mysterious. Each new survey reveals more filaments, more hidden structures, more vast connections between regions once thought separate. Even our own supercluster, Laniakea, is just one part of a larger flow that holds Ophiuchus, Perseus Pisces, and countless other superclusters together, forming what may be the universe's ultimate pattern, a single continuous structure connecting nearly everything that exists. The Ophiuchus Supercluster, a giant among giants. The Ophiuchus Supercluster lies about 390 million light-years from Earth, deep within the constellation of Ophiuchus, a region of the sky often overlooked but home to some of the universe's most powerful and mysterious structures. To the naked eye, Ophiuchus appears as a faint patch among the stars, but hidden behind it is an enormous concentration of galaxies bound together by gravity, forming one of the largest superclusters known in our cosmic neighborhood. Its sheer mass, scale, and complexity make it a kind of galactic metropolis, a colossal junction in the cosmic web. From our vantage point, the Ophiuchus supercluster sits not far, in cosmological terms, from other great nearby structures, such as the Shapley concentration and our own Laniakea supercluster. It occupies a region of the sky that stretches across hundreds of millions of light-years and contains several major galaxy clusters. The galaxies within it are arranged along invisible threads of dark matter, forming chains and knots that give the Ophiuchus supercluster its intricate structure. When astronomers first began mapping this region, it was difficult to see what was there. The Ophiuchus constellation lies close to the plane of the Milky Way, where dust and gas obscure much of the distant universe. This zone of avoidance, as astronomers call it, has long hidden vast regions of the cosmos behind our own galaxy's bright stars and dense clouds. But through the use of X-ray and radio telescopes, scientists were able to peer through this veil, revealing one of the most massive concentrations of matter in the local universe. What they found was extraordinary, a supercluster so dense and energetic that it rivals the famous Shapley supercluster in scale and mass. At the heart of the Ophiuchus supercluster lies the Ophiuchus cluster. It is one of the brightest and most massive X-ray sources in the sky, glowing with the heat of gas that has been compressed and heated to tens of millions of degrees. This gas fills the space between galaxies, creating an atmosphere of superheated plasma that gives off intense radiation detectable even across hundreds of millions of light-years. The central galaxy of the cluster, a giant elliptical, anchors the system with a supermassive black hole at its core, an engine powerful enough to shape its environment on colossal scales. The cluster is surrounded by numerous smaller groups and filaments of galaxies, each moving under the influence of the supercluster's gravitational field. These structures are not static, they are slowly drifting, merging and reshaping themselves as dark matter pulls them into new configurations. To imagine its scale, consider that light, traveling at nearly 300,000 kilometers per second, would take hundreds of millions of years to cross it. Within this region lie thousands upon thousands of galaxies, each containing billions of stars, planets, and possibly countless worlds. The combined mass of all these galaxies, their dark matter halos, and the intergalactic gas makes the Ophiuchus Supercluster one of the dominant structures in the local cosmic landscape. Like other superclusters, Ophiuchus is not bound together permanently. Over billions of years, the cosmic fabric itself will stretch, gradually isolating its clusters from one another. But for now, these structures remain part of a connected whole, a massive hub in the great network of filaments that make up the nearby universe. Mapping the Ophiuchus Supercluster has not been easy. The dust of the Milky Way blocks visible light from many of its galaxies, forcing astronomers to rely on X-ray, radio, and infrared observations. By combining these data, scientists have pieced together a clearer image of the region, revealing a massive structure extending across more than 300 million light-years. The galaxies in the supercluster are spread out along filaments that link them to other major superclusters. These filaments form the cosmic highways that feed the Ophiuchus region with fresh gas and galaxies, keeping it active and evolving. Astronomers studying Ophiuchus describe it as a bridge between the dense, crowded regions of the local universe and the more distant, sparsely populated areas beyond. Because it lies relatively close to the Milky Way, it offers a rare opportunity to study how such immense systems behave in detail. Observations have shown that the supercluster's central regions are dominated by massive, elliptical galaxies, ancient systems that formed early in cosmic history. Surrounding them are younger spiral galaxies, still rich in gas and actively forming stars. This diversity reflects the different evolutionary stages of galaxies depending on where they sit within the supercluster's structure. Those near the dense core experience frequent interactions and mergers, while those along the outer filaments evolve more slowly and in isolation. Simulations suggest that dark matter filaments extend far beyond the visible galaxies, linking Ophiuchus to other nearby superclusters and clusters. These hidden bridges act as conduits through which matter flows, feeding the dense regions at the supercluster's core. The galaxies we see today are only the bright traces of this larger, unseen framework. The Ophiuchus Supercluster also helps astronomers understand the transition between local and large-scale cosmic structures. It sits near the boundary between the Laniakea Supercluster and the Hercules Supercluster. Some studies suggest that the flow of galaxies in this region may be influenced by both, hinting at an even larger scale pattern of motion that spans hundreds of millions of light-years. In this way, Ophiuchus acts as both a massive structure in its own right and a connecting node in the cosmic web that binds our universe together. The galaxies within Ophiuchus are not merely passengers. They are active participants in its history. Many of them bear the marks of past collisions, distorted shapes, long tidal tails, and regions of intense star formation triggered by gravitational encounters. Galaxy clusters within the supercluster are still merging, releasing shockwaves that ripple through the intergalactic medium. These events heat the surrounding gas and can trigger further bursts of star formation, driving the cycle of cosmic evolution forward. Even the faint background glow of X-rays and radio waves in this region tells a story of violence, motion, and change, the ongoing drama of galaxies shaped by the forces that govern the universe itself. Because of its mass and activity, the Ophiuchus Supercluster has become a crucial laboratory for studying the interplay between matter, dark matter, and energy on the largest scales. By observing how galaxies and gas behave within it, scientists gain clues about how gravity sculpts the universe and how dark energy drives its expansion. The intense X-ray emissions from the Ophiuchus cluster, for instance, provide valuable data about the temperature and density of intergalactic gas, revealing how matter behaves under extreme conditions. Likewise, radio observations expose the aftermath of ancient black hole eruptions and the vast magnetic fields that thread through the supercluster's space. From our small corner in the Milky Way, the Ophiuchus Supercluster may seem unimaginably far away, but on cosmic scales, it is close, a neighboring realm of galaxies whose influence quietly extends toward us. Its presence reminds us that even our local universe is part of something much greater, a web of colossal structures, each one a testament to the slow, steady work of gravity across cosmic time. A quiet giant, until it wasn't. It began with faint irregularities. As X-ray observatories such as NASA's Chandra Telescope and the European Space Agency's XMM Newton began peering into the Ophiuchus cluster, astronomers noticed subtle distortions in its diffuse glow. The X-ray brightness wasn't uniform. Instead, it seemed to ripple, as though the hot plasma filling the cluster had been stirred or disturbed. The edges of this glow were oddly shaped, almost curved, as if immense waves had passed through the gas long ago. These weren't the signs of a tranquil system in equilibrium. They were scars, written across millions of light-years of space. At first, scientists were cautious. Galaxy clusters are dynamic places where mergers, collisions, and black hole activity constantly reshape the environment. Gas sloshing and turbulence are not unusual, but the scale of the disturbance in Ophiuchus seemed far larger than anything seen before. The X-ray data showed a vast faint cavity, a region where the hot gas appeared to have been pushed aside. It wasn't just a small pocket of emptiness. It was a colossal bubble, hundreds of thousands of light-years wide. As astronomers examined the data, the shape of the cavity became clearer. It appeared offset from the cluster's center, like a hollowed-out crater carved into the surrounding plasma. This wasn't something caused by gravitational motion alone. Something had blasted outward from the cluster's heart, displacing gas on a scale that dwarfed the entire Milky Way. To understand what could have done this, researchers turned their attention to the cluster's central galaxy. In most galaxy clusters, the central galaxy acts as a kind of gravitational anchor. At its core lies a black hole that occasionally flares to life, feeding on gas and dust and releasing energy in the form of powerful jets. These outbursts, while violent, are usually modest by cosmic standards. They heat the surrounding gas, regulate star formation, and help maintain the delicate balance within the cluster. But in Ophiuchus, something had gone far beyond that ordinary cycle of activity. Using combined observations from X-ray and radio telescopes, scientists pieced together the evidence. The cavity observed in the cluster's X-ray glow aligned perfectly with faint radio emissions, a telltale sign of charged particles accelerated by a past explosion. These emissions revealed that the cavity was filled with radioplasma, the remnant of a titanic eruption that had blasted through the cluster hundreds of millions of years ago. What they were looking at wasn't just another example of black hole feedback. It was the aftershock of the most powerful known explosion since the Big Bang. When the full scale of the event was calculated, the results were staggering. The eruption had released hundreds of thousands of times more energy than any supernova and several times more than the previous record holder, an outburst in the galaxy cluster MS0735.6 plus 7421. The total energy output was so vast that it could have powered every star in the Milky Way for several billion years. It was as if a cosmic volcano had erupted from the heart of the Ophiuchus cluster, blasting matter outward with a force capable of reshaping the surrounding space. The explosion had left behind a cavity roughly 1.5 million light-years wide, large enough to fit 15 Milky Ways side by side. What made this discovery even more remarkable was how easily it could have gone unnoticed. Only through the penetrating gaze of X-ray and radio telescopes could astronomers see what was truly happening. To an optical telescope, Ophiuchus still looked calm, its galaxies faintly shimmering against the darkness. But in other wavelengths, it was revealed as a site of unimaginable violence, a region forever marked by an ancient cosmic detonation. The cause of this eruption likely came from the cluster's central supermassive black hole. At some point in the distant past, it must have entered an active phase, feeding on enormous amounts of gas and releasing jets of relativistic particles that tore through the surrounding plasma. These jets would have expanded rapidly, pushing the hot gas outward and forming the massive cavity that we see today. When the jets finally shut off, they left behind a region filled with low-density, magnetized plasma, the faint radio glow that astronomers detected millions of years later. What's astonishing is that such an event could occur without destroying the cluster itself. Despite the unimaginable energy released, the Ophiuchus cluster remained intact. The eruption was powerful enough to blow a hole through its atmosphere, yet not so strong that it tore the entire system apart. This suggests a delicate balance between creation and destruction. The same black hole that devastated its surroundings also prevented runaway cooling in the cluster's core, helping to regulate the flow of matter over cosmic timescales. It's a strange paradox of the universe. The most violent forces can also bring about long-term stability. For years, the clues to this eruption lay buried in the data, dismissed as minor irregularities or instrument noise. It wasn't until researchers combined data from multiple observatories, Chandra for X-rays, XMM Newton for confirmation, and radio data from observatories in Australia and India, that the full picture emerged. When they overlaid the different images, the alignment between the X-ray cavity and the radio lobe was unmistakable. This was no ordinary feature. The size, shape, and energy all pointed to a single explosive event unlike anything seen before. In that moment, what had seemed like a quiet, stable cluster was revealed as a record of cosmic violence on the grandest possible scale. The discovery rewrote how scientists thought about galaxy clusters and black hole activity. Until then, it was assumed that even the most massive black holes could only release a limited amount of energy before stabilizing. The Ophiuchus eruption shattered that assumption. It proved that black holes could, under the right conditions, unleash bursts so powerful that they reshape the space around them on scales of millions of light years. Such events are rare. Perhaps only a few occur in the entire universe every billion years, but they have lasting consequences. They redistribute gas, alter the growth of galaxies, and influence how matter cools and collapses in the cluster's core. Even today, the aftermath of the explosion continues to ripple through the Ophiuchus Supercluster. The displaced gas is slowly falling back toward the center, creating turbulence and shock waves that propagate through the cluster's atmosphere. These ripples, similar to sound waves traveling through air, may persist for hundreds of millions of years, gradually dissipating as they spread. In a sense, the Ophiuchus cluster still echoes from the violence of its past, a cosmic memory recorded in the faint hum of X-rays and radio waves that reach us across the void. What happened in Ophiuchus may not be unique, but it is one of the clearest and most dramatic examples of how active galactic nuclei shape the cosmos. It demonstrates that even regions that appear quiet and stable can hide evidence of immense power, waiting to be uncovered by the right instruments and the right questions. Every distortion in the data, every faint arc of radio light may tell a story of cosmic upheaval waiting to be understood. The realization that Ophiuchus was once the site of the largest known explosion changed how astronomers view the hidden forces at work within superclusters. These colossal systems are not merely static gatherings of galaxies. They are dynamic environments, alive with energy and transformation. Black holes, invisible and silent for most of their lives, can awaken in an instant, unleashing bursts that reshape the fate of entire clusters. What once seemed like a quiet giant had, in truth, survived an eruption of nearly unimaginable power. A reminder that even in the vast stillness of the cosmos, nothing remains truly calm forever. A blast across billions of years. When astronomers talk about the Ophiuchus explosion, it's easy to imagine something like a sudden cosmic detonation, a burst of unimaginable force that happened all at once. but that picture isn't quite right. In the universe, explosions don't behave the way we understand them on Earth. There's no sharp flash, no deafening boom racing outward through air. There's only the slow motion of space itself being stirred, molded, and pushed by invisible energy over eons. What we call an explosion, in cosmic terms, is more like a long breath, a release of power so vast that even the fastest events take millions of years to play out. The eruption in the Ophiuchus cluster unfolded across a span of time that's almost beyond human comprehension. Scientists estimate that it lasted hundreds of millions of years, possibly even close to 1 billion. Over that period, the central black hole of the cluster steadily injected energy into the surrounding gas, blowing vast bubbles outward in slow motion. Imagine a balloon being inflated, not in seconds, but over the entire history of mammals on Earth. That's roughly the pace of change the Ophiuchus cavity experienced. Every year, the shock front advanced only a few light-years, a barely perceptible ripple in a cluster nearly 15 million light-years across. From the perspective of human civilization, the event was effectively frozen in time. If we had watched Ophiuchus from its beginning, we would have seen nothing dramatic within a human lifetime. There would have been no sudden transformation. The cluster would have looked serene and unchanging. And yet, hidden beneath that calm, the black hole's jets were continuously sculpting the cosmos, displacing trillions of tons of hot gas and slowly carving a cavity the size of multiple galaxies. To truly grasp this kind of timescale, we need to stretch our imagination. The entire recorded history of human civilization, every empire, every invention, every generation, fits within just a few thousand years. The Ophiuchus eruption lasted perhaps 100,000 times longer. From the first stirrings of multicellular life in Earth's oceans to the rise of humanity, this cosmic engine would have been steadily at work, reshaping the cluster in complete silence. Even by the universe's own standards, this was a long and sustained release of energy. The process began, as most such outbursts do, with the feeding of the central black hole. In normal circumstances, a supermassive black hole consumes gas and dust at a modest rate, radiating only faintly as material disappears beyond its event horizon. But in Ophiuchus, something tipped the balance. The black hole suddenly had access to an enormous supply of fuel, and it began converting that mass into energy with extraordinary efficiency. Instead of swallowing all the gas, magnetic fields around the black hole funneled part of it into twin jets that shot outward along its rotational poles. These jets, traveling close to the speed of light, blasted through the cluster's atmosphere, heating it and pushing it aside. The energy carried by the jets wasn't released in a single instant, but continuously, like a blowtorch rather than a bomb. Over tens or hundreds of millions of years, the jets inflated vast lobes filled with high-energy particles and magnetic fields, hollowing out the giant cavity now seen in X-ray maps. Each moment of that process was gentle by human standards, but add them all together, and the result was the single largest explosion ever observed. The amount of energy released every second may have been roughly equivalent to a few supernova, already immense, yet sustained over 1 billion years. The cumulative total became staggering. It was enough to heat and move entire clouds of plasma millions of light-years wide. What's striking is how quiet such a process would seem if we could witness it up close. There's no sound in space. The cluster's thin gas is far too diffuse to carry vibration. The only noise would come in the form of radiation. Radio waves, X-rays, gamma rays, each flickering faintly against the cosmic background. The jets would appear as faint, narrow streams glowing in radio light, slowly changing their shape as they interacted with surrounding gas. It would be an event both unimaginably violent and eerily calm, like watching a slow tidal wave of energy move through molasses. The slow pace of cosmic change often deceives us into thinking the universe is static, but Ophiuchus is proof that even the largest structures are constantly in motion, just on timescales that dwarf our senses. What we see as a still image of the cluster is, in reality, just a single frame in a story that has been unfolding for hundreds of millions of years. Every photon of light we detect today left its source before modern humans even existed. By the time it reaches us, the actual cluster may have evolved in ways we can only guess. To visualize this, imagine compressing the history of the Ophiuchus eruption into a single year. In that case, each day would represent millions of years. The black hole would ignite on January 1st, beginning to push jets of plasma outward. By June, the cavity would only start to form, still small and faint. In August, the surrounding gas would begin to glow from the heat of compression. By December, as the year draws to a close, the cavity would reach its enormous size, and only then would the energy begin to fade. That one cosmic year would represent nearly 1 billion real years. This immense timescale also affects how astronomers study such phenomena. Because they evolve so slowly, direct observation of change is nearly impossible. Instead, scientists must piece together clues from snapshots of different systems at different stages, building a timeline from comparison. One galaxy cluster might show a newly ignited jet. Another might display a fully formed cavity. A third might reveal only a fading relic. Together, they form a cosmic time-lapse, reconstructed from the static pictures of countless clusters scattered across the sky. The after effects of the Ophiuchus eruption continue to echo today. The cavity is still filled with magnetic fields and relativistic particles, which slowly decay and cool as they drift outward. The surrounding gas remains hotter than it should be, evidence of the ancient heat injected into it. For hundreds of millions more years, the scars of this eruption will persist, subtle distortions in temperature, density, and motion that future astronomers may still be able to detect. This endurance is one of the most fascinating aspects of cosmic events. They outlast everything. On Earth, even the greatest explosions fade in moments and their traces vanish in centuries. But in space, time itself seems slower. Shockwaves ripple for millions of years. Energy released in an instant takes eons to dissipate. Every structure, from galaxy clusters to the cosmic web itself, carries memories of forces that acted long ago. The Ophiuchus cavity is one such memory, frozen in the fabric of the universe. Our sense of long, decades, centuries, even millennia, barely registers in the universe's rhythm. To it, our entire existence is no more than the blink of an eye. The Ophiuchus explosion, by contrast, is a symphony still resonating through the cluster's hot gas. When we detect its echo in our telescopes, we are not watching a past event as much as we are witnessing a process still unfolding, its tail end stretching across cosmic history, the supermassive black hole behind the curtain. At the very heart of the Ophiuchus cluster lies the supermassive black hole, Ophiuchus A. It's easy to picture black holes as endlessly devouring, eternally destructive things, but for much of their lives, they are almost completely silent. They sit in the centers of galaxies, invisible and still, surrounded by vast clouds of gas and stars. In their quiet phases, even though their gravity rules over hundreds of billions of suns, they emit almost no light, giving no hint of their presence. Yet, under the right conditions, these sleeping giants can awaken, and when they do, the results can reshape entire regions of space. The black hole in Ophiuchus is estimated to be several 100 million times more massive than the Sun. To put that into perspective, if it replaced the Sun at the center of our solar system, its event horizon, the invisible boundary where gravity becomes inescapable, would stretch beyond the orbit of Mercury. Its mass is so great that not even light can escape it. But paradoxically, some of the brightest things in the universe are powered by black holes, just like this one. Their light comes not from the black holes themselves, but from the matter falling toward them, an inward spiral of energy and chaos. Astronomers believe that Ophiuchus A's black hole was once in one of these active phases. Perhaps a nearby galaxy drifted too close, its gas drawn in by Ophiuchus A's immense gravity. Or perhaps a slow buildup of material from the cluster's surrounding medium finally tipped the balance, sending torrents of gas streaming inward. As this matter fell toward the black hole, it didn't simply vanish. Instead, it formed a vast accretion disk, a swirling ring of plasma heated to unimaginable temperatures by friction and magnetic forces. The energy released from this infall was extraordinary. A fraction of the matter's mass was converted directly into radiation, in line with Einstein's famous equation, E equals mc squared. Even a small amount of mass could release more energy than billions of nuclear bombs. But not all of that energy escaped as light. Much of it was funneled into two narrow jets that blasted out from the black hole's poles. These jets are among the most powerful structures in the universe, streams of charged particles moving at nearly the speed of light, guided by tangled magnetic fields. In smaller galaxies, such jets can stretch for thousands of light years. In galaxy clusters like Ophiuchus, they can reach millions. It was these jets, astronomers believe, that created the immense cavity discovered in 2020. What makes such an event remarkable is how it blurs the line between creation and destruction. The black hole didn't simply consume, it also sculpted. By injecting energy into the cluster's gas, it prevented that gas from cooling too quickly and collapsing into new stars. It altered the balance between gravity and pressure, slowing down the evolution of galaxies within the cluster. This feedback mechanism is now understood to be a key part of how galaxies and clusters evolve. When a black hole grows too active, it blasts out so much energy that it starves itself, driving away the very material that feeds it. Once the gas cools and drifts back in, the process begins again. It's a cycle of dormancy and eruption, silence and violence. Ophiuchus's black hole likely followed this same rhythm. For hundreds of millions of years, it may have been dormant, then suddenly awakened, releasing a storm of energy that filled the cluster. Eventually, the jets weakened, the accretion disk thinned, and the black hole fell quiet once more, leaving behind only the vast scar that we observe today. To understand how such jets are launched, scientists turn to one of the most extreme environments in nature, the region just outside the event horizon. Here, space and time are twisted by the black hole's rotation. Magnetic fields, anchored in the swirling plasma, become tightly wound, channeling energy outward like a spring being released. This process, known as the Blandford-Znajek mechanism, allows the black hole's spin to convert directly into kinetic energy. In effect, the black hole's rotation powers its own eruption. The faster it spins, the more energy it can unleash. The black hole in Ophiuchus A might have been spinning rapidly during its active phase, possibly near the speed of light at its equator. That spin would have provided an enormous reservoir of energy, enough to drive the jets for hundreds of millions of years. Over time, the jets would have grown unstable, bending and twisting as they interacted with the surrounding gas, inflating the cavity that now stands as evidence of their ancient fury. Despite the scale of its power, the black hole itself would have remained tiny compared to the cluster it influenced. Its entire event horizon could fit comfortably within the orbit of a star system, yet it managed to affect regions stretching across millions of light years. This is one of the universe's great paradoxes. The smallest and densest objects can shape the largest and most diffuse structures. In the aftermath of the eruption, Ophiuchus A would have appeared very different. The galaxy around the black hole may have been flooded with radiation, its interstellar gas blasted away or superheated. New stars would have struggled to form, and existing ones might have been stripped of their outer layers. The entire central region of the cluster would have glowed in X-rays, a sign of the searing temperatures left behind. Gradually, as the energy dissipated, the cluster would have settled into a quieter state, the cavity cooling and filling with radio-emitting plasma. Even in its silence, the black hole's influence continues. The surrounding gas still bears its fingerprints, subtle motions, temperature gradients, and magnetic ripples that trace the paths of the old jets. Astronomers can study these relics to infer the black hole's history, much like geologists reading the layers of rock left by ancient eruptions on Earth. Each layer tells a story of activity and rest, of feeding and starvation, of a cosmic engine that has shaped its surroundings for billions of years. What's truly humbling is how black holes like this one operate on scales that defy the limits of human time and experience. The black hole's life cycle stretches across epochs, influencing the universe long after stars are born and die. Even now, Ophiuchus A's black hole may be stirring again, its accretion disk beginning to brighten, its jets preparing for another awakening. If that happens, it will be another chapter in a story that has already lasted longer than life on Earth itself. The eruption that once tore through Ophiuchus is gone, but the engine behind it, the black hole itself, remains patient and still, waiting for the next moment when gravity, matter, and time align to awaken it once more. Measuring the unmeasurable. How do you measure something so vast, so distant, and so old? The explosion they were trying to understand had unfolded hundreds of millions of light years away, across a timescale far beyond any human reference. There was no direct light from the event itself, no visible flare or expanding debris like those seen in supernovae. All that remained were the faintest of scars. From those subtle clues, scientists had to reconstruct one of the most powerful cosmic events ever recorded. The process began with a telescope that doesn't see invisible light. The Chandra X-ray Observatory, orbiting Earth since 1999, was built to study the universe in X-rays, a range of light produced by the hottest and most energetic regions in space. Galaxy clusters like Ophiuchus glow in X-rays because their intergalactic gas is heated to tens of millions of degrees. In those glowing halos, astronomers can read the hidden dynamics of cosmic activity, where gas is dense, where it's thin, where it's been pushed aside, and where something violent might have happened long ago. When Chandra observed the Ophiuchus cluster, instead of a smooth, elliptical glow of hot gas, as most clusters show, there was a strange curved boundary on one side of the image, a faint edge where the X-ray emissions suddenly dropped. That feature hinted that something had blown a massive bubble into the cluster's atmosphere. But the data alone couldn't reveal how large it was. To confirm it, astronomers compared it with earlier X-ray maps taken by XMMM Newton Observatory, another space telescope that specializes in detecting high-energy light. XMMM Newton's wider field of view allowed them to trace the faint outline of the cavity even further, revealing that it wasn't just large, it was colossal. The cavity stretched across 1.5 million light-years. It looked as though a massive invisible hand had scooped out a section of the Ophiuchus cluster, leaving behind a hollow in the sea of superheated plasma. The next question was obvious. How much energy would it take to move that much material? To answer that, astronomers turned to physics. Hot gas in galaxy clusters behaves like a fluid, and when something displaces it, the resulting cavity leaves a measurable signature. By calculating the pressure and volume of the gas around the cavity, scientists can estimate the total work done to create it, essentially the amount of energy released during the eruption. In this case, they multiplied the pressure of the surrounding gas by the volume of the cavity, a calculation that, while simple in concept, involved enormous numbers. The result was staggering. The energy required to form the Ophiuchus cavity was around 5 multiplied by 10 to the power of 61 ergs, roughly equivalent to hundreds of millions of gamma-ray bursts, or 5 times more powerful than the previous record holder, found in the MS0735 cluster. But energy doesn't just come from nowhere. That's when the data began to point back to Neve 1 and its supermassive black hole. The cavity's direction matched the orientation of faint radio jets seen by telescopes such as the Giant Meter Wave Radio Telescope in India and the Murchison Wide Field Array in Australia. These radio observatories don't look for light. They detect long-wavelength electromagnetic signals emitted by electrons spiraling through magnetic fields. When combined with X-ray images, the radio data completed the picture. In a sense, it was like uncovering a fossilized explosion. The event had ended, but its imprint remained etched into the cluster, perfectly preserved in the energy fields of space. By comparing the brightness and shape of these radiolobes with models of jet behavior, astronomers could estimate how long the eruption had lasted. These findings didn't come easily. Detecting signals from hundreds of millions of light-years away is like trying to hear the echo of a whisper across an ocean. The X-ray data from Chandra consisted of individual photons collected over hundreds of hours of exposure. Each photon was a precious clue, carrying information about the energy and location of the emission. Astronomers spent years refining the images, filtering out background noise, and combining multiple observations to sharpen the picture. The radio data, too, required careful calibration. Ground-based observatories are affected by Earth's atmosphere, local interference, and cosmic background radiation. Extracting the faint trace of ancient radio lobes from all that noise required both patience and technology that didn't even exist when the explosion first began. When scientists first noticed the curvature in the X-ray image, they assumed it was a data artifact, maybe a calibration issue or a quirk in the imaging process. Only after years of follow-up observations, using multiple telescopes in different wavelengths, did the evidence become undeniable. The technique used to measure the energy of such eruptions relies on combining multiple kinds of data, much like layering transparencies on top of one another. X-ray data reveal the density and temperature of the gas. Radio data show where relativistic particles, those moving near the speed of light, are located. In some cases, optical and infrared images are added to identify which galaxy or black hole might be responsible. By combining all these, astronomers can build a three-dimensional model of what happened, tracing how the jets expanded, how the gas reacted, and how the structure evolved over time. Through this process, the Ophiuchus eruption began to take shape as it became a benchmark for understanding extreme black hole feedback. Until then, astronomers believed there might be upper limits to how powerful such events could be. The Ophiuchus data shattered that assumption. It suggested that supermassive black holes, under the right conditions, could release energy on scales comparable to the total output of entire clusters. A single object, only a few 100,000 kilometers across, had managed to rearrange a region of space millions of light-years wide. Every calculation of energy or distance represents an attempt to bridge the human and the cosmic. Our instruments built on Earth are tiny compared to the distances they probe, yet they can read the faint X-ray breath of an explosion that happened before humans existed. When astronomers measure an event like the Ophiuchus eruption, they're reaching backward through time, decoding an echo that has traveled across the universe for hundreds of millions of years before landing on the sensors of a satellite orbiting our planet. And even with all our precision, there's still uncertainty. The numbers carry margins of error. The models depend on assumptions about gas density, temperature, and cluster geometry. Some researchers suggest that the energy could be even greater than the official estimate, while others argue it might be somewhat lower. Yet no one disputes the scale. It was a cosmic outburst of incomprehensible magnitude, one that challenges the limits of what black holes, and the universe itself, are capable of. Each X-ray photon and each radio wave is a letter in that ancient narrative. Together, they reveal not just the power of one black hole, but the hidden dynamics of the universe itself. A universe that records everything it does, even its greatest explosions, in the quiet glow of its distant galaxies. Visualizing the impossible. If human eyes could somehow perceive X-rays, the Ophiuchus cluster would look like a gently shimmering nebula of turquoise and violet light, with faint filaments and knots where the gas is denser. At its center, the dark void of the explosion would dominate the scene, outlined by arcs and ripples of brighter emission. From a great distance, it might resemble an enormous wound, a silent circular cavity against a glowing background of energy. It would be hauntingly beautiful, but also deeply unsettling. The eruption's light itself wouldn't have been blinding. The gas in the cluster isn't dense enough to glow in a way our eyes could see, even when heated to tens of millions of degrees. Instead, it would have emitted mostly X-rays and radio waves, the language of cosmic giants. The few visible light galaxies embedded in the cluster would have carried on as if nothing extraordinary were happening around them, their stars orbiting, their spiral arms slowly turning. The violence unfolding in the intracluster medium would have been entirely invisible to anyone standing on one of their worlds. And yet, from a radio telescope's perspective, the scene would be alive with structure. The radio lobes created by the eruption would glow with a faint, ghostly light stretching over millions of light years. Telescopes, like the Very Large Array in New Mexico, have detected these lobes. Visualizing those jets requires another leap of imagination. To witness it in real time would be impossible, but imagining it as a time-lapse across billions of years brings it to life. You'd see the cluster as a living system, galaxies slowly drifting, gas flowing between them and at the center, pulses of energy spreading like the rings of an endless tide. Each wave would push the hot plasma outward, cooling and expanding as it went, until the entire cluster's shape subtly shifted. The result would not be chaos, but an almost graceful evolution, a kind of cosmic breathing. When scientists translate these findings into visualizations, they often use false color composites, blending X-ray, radio, and visible data. In these images, the invisible becomes visible, the X-ray glow of hot gas, the radio lobes stretching outward like ghostly wings, and the faint galaxies sprinkled throughout. The result is not a literal picture, but a map of energy. It shows us where the universe stores its heat, its motion, its turbulence. It's an image of processes that would otherwise remain forever hidden. These visualizations also serve to remind us of how limited our senses are. The universe doesn't radiate primarily in visible light. Most of its drama unfolds in wavelengths we can't see or feel. Without X-ray and radio telescopes, the Ophiuchus cluster would appear inert. Only by extending our perception with machines can we glimpse the true range of cosmic phenomena. Each telescope, in that sense, is not just an instrument, it's a prosthetic for the imagination. To see the Ophiuchus eruption, then, is really to understand it through data, through color maps, through the subtle differences in brightness that instruments detect across wavelengths. Every pixel in a Chandra image represents photons that have traveled hundreds of millions of years to reach us. By assembling them into patterns, we reconstruct a story written in light and time. It's humbling to think that somewhere deep in that void, the final wisps of the eruption are still radiating. Space may be vast and empty, but it remembers. Trying to visualize that is to brush against the limits of comprehension. The power source, feeding the beast. Normally, black holes are silent consumers, but sometimes they overfeed. The process that powers the most energetic events in the universe begins not with destruction, but with excess. When too much matter falls toward a black hole too quickly, it forms a swirling accretion disk. Ophiuchus A likely went through this phase on an unimaginable scale. Over time, gravity guided the gas inward, slowly feeding the black hole. But this was not a steady process. Like a clogged engine that suddenly clears, the flow of material could have built up pressure, then suddenly ignited. When gas flows toward a black hole, some of it inevitably spirals too close and is swallowed. Yet a fraction is caught up in the chaotic magnetic fields of the accretion disk. These fields act like cosmic springs, storing and redirecting energy. When they reconnect, when tangled lines snap and reform, they can hurl material outward at nearly light speed. The black hole becomes, in a sense, a particle accelerator. Over time, this process can repeat in cycles. The black hole feeds, releases, quiets, then feeds again. Each cycle can last millions of years. During the Ophiuchus event, it's thought that one of these cycles went out of balance, perhaps because a particularly dense flow of gas reached the center. In that moment, the black hole's magnetic and rotational energy were unleashed in a violent outburst. The feeding mechanism behind such power is an elegant interplay of gravity, heat, and magnetism. As matter falls in, its gravitational potential energy, the energy stored by its position in a gravity field, is converted into kinetic energy and heat. This heat radiates outward in X-rays and gamma rays, but it also drives turbulence within the accretion disk. Magnetic fields amplify, threading through the hot plasma, and when those fields become twisted enough, they erupt outward, carrying some of the infalling material along with them. The process can even tap into the rotational energy of the black hole. The magnetic field anchored in the surrounding disk acts as a conduit, draining rotational energy and converting it into outward jets. In the case of Ophiuchus, it's likely that both processes, accretion-driven heating and spin extraction, played roles. The black hole may have been spinning near its theoretical maximum, which would mean that even a small magnetic imbalance could trigger an enormous jet. Once the outflow began, it would have propagated outward through the galaxy's halo, inflating bubbles of relativistic plasma. These bubbles then expanded into the hot intra-cluster medium, displacing it like a piston in a vast cosmic engine. Even long after the jet subsided, the bubbles would continue to rise and expand, powered by the residual energy trapped within them. Using radio telescopes, astronomers detect faint synchrotron radiation, a signature of electrons spiraling through magnetic fields, coming from the cavity's edges. This radiation is a ghostly echo of the event that once was. It reveals the boundaries where energy met resistance, where heat met density. In some sense, it's an act of cosmic metabolism. The black hole takes in energy, releases it in a violent purge, then rests. Feeding, heating, exploding and resting, this rhythm has shaped galaxies since the dawn of the universe. Comparing giants, MS 0735.6 plus 7421. Long before the Ophiuchus Supercluster stunned astronomers with its enormous cavity, another giant held the title for the largest known explosion in the universe. It was the Galaxy cluster MS 0735.6 plus 7421, a system roughly 2.6 billion light-years away in the constellation Camelopardalis. For nearly 2 decades, it was considered the ultimate example of what happens when a supermassive black hole goes on a feeding frenzy. To understand why Ophiuchus became such a breakthrough, it helps to revisit what made MS 0735.6 plus 7421 so remarkable in the first place. When astronomers discovered its enormous cavities in 2005 using NASA's Chandra X-ray Observatory, they were astonished. The central black hole in that cluster's dominant galaxy had apparently blasted out twin jets of high-energy particles that carved out enormous holes in the surrounding gas, each bubble over 1 million light-years across. These cavities were surrounded by bright rims of hot gas, marking where shock waves had swept through the cluster's plasma. The energy required to inflate those cavities was almost unthinkable. Scientists estimated that the outburst lasted around 100 million years, meaning the black hole must have been pumping out continuous energy for a period longer than the time it takes our solar system to orbit the Milky Way once. At the time, nothing else in the known universe came close to matching it. But then came Ophiuchus. When astronomers began analyzing its X-ray and radio data in 2020, they recognized a familiar pattern. Cavities in the hot gas surrounding the cluster's core, just like in MS 0735.6 plus 7421. What truly distinguishes Ophiuchus is not just the total energy released, but the way it was released. In MS 0735.6 plus 7421, the eruption appears to have been powerful, but relatively straightforward. A pair of jets emerging from a central black hole, inflating symmetric lobes in the surrounding gas. In Ophiuchus, the eruption seems more complex, involving an asymmetric cavity and unusual distortions in the gas that suggest a more chaotic process. It's possible that Ophiuchus experienced multiple overlapping outbursts, or that the jets precessed, slowly changing direction over time, carving out an irregular void rather than 2 clean lobes. Astronomers have also noted that the Ophiuchus cavity appears to have expanded farther than the jets of MS 0735.6 plus 7421 could have managed on their own. This implies that the energy wasn't released in one short, focused burst, but rather through a slow, persistent injection of power over an extremely long period. The eruption may have lasted for hundreds of millions of years, making it less an explosion and more a sustained cosmic storm. Such a process would have required the central black hole to keep accreting matter at a steady rate for an extraordinary length of time, something rarely seen even in the most active galaxies. The environments of the two clusters also differ significantly, which adds another layer of comparison. MS 0735.6 plus 7421 lies in a much more distant and younger part of the universe where galaxy clusters were still forming and colliding frequently. Ophiuchus, by contrast, is relatively close and part of a more mature cosmic region. Its gas reservoir has likely been stable for billions of years, meaning that an eruption of such power had to overcome enormous gravitational confinement. In other words, for Ophiuchus to carve such a cavity, it had to push against denser and more resistant material, implying an even greater energy release than the raw size of the cavity might suggest. In MS 0735.6 plus 7421, the cavities are surrounded by shock fronts that still glow brightly in X-rays, evidence of the powerful waves that once tore through the gas. But the Ophiuchus cavity is more extreme. The gas has been displaced so dramatically that it looks as though part of the cluster's core was ripped open. The event seems to have not only heated the gas, but restructured the entire cluster's interior. Until its discovery, most models assumed that black hole outbursts could regulate cluster gas, but not completely rearrange it. Ophiuchus forced astronomers to reconsider that assumption. If one black hole could release this much energy without tearing itself apart, then black hole feedback may be capable of far more dramatic effects than anyone thought. It may even play a role in shaping the large-scale structure of the cosmic web itself. Both eruptions were likely driven by similar mechanisms, but the efficiency of that process appears to differ. In Ophiuchus, the conversion efficiency must have been astonishingly high. The black hole was somehow able to release a greater fraction of its available energy into the surrounding environment. That raises questions about whether spin played a role. A rapidly rotating black hole can tap into its own rotational energy through the Blandford-Znajek mechanism, effectively turning itself into a cosmic dynamo. If Ophiuchus A had an exceptionally high spin, that could explain why its eruption was so much more powerful. The differences between the two also provide insight into timing. In MS 0735.6 plus 7421, the eruption's effects appear to have largely settled. The cavities are now buoyantly rising away from the cluster's center, like bubbles drifting upward in water. In Ophiuchus, the cavity still glows intensely, suggesting that the gas remains hotter and the structure younger in relative terms. This gives astronomers a chance to study different stages of the same phenomenon, one ancient and cooling, the other still radiating the energy of its youth. Together they form a kind of cosmic timeline for black hole outbursts. When researchers overlay X-ray maps of Ophiuchus and MS 0735.6 plus 7421, the scale of both events becomes clear. Each cavity represents a region where gravity and energy collided in a way that transformed an entire cluster. The symmetry of MS 0735.6 plus 7421 contrasts with the raw, almost chaotic nature of Ophiuchus. One looks like a precise experiment, the other like an act of cosmic fury. Yet both were powered by the same type of object. In this comparison, Ophiuchus stands as the next chapter in a growing pattern. Each discovery reveals a larger and more extreme example of the same process, suggesting that we may not have reached the true upper limit of black hole feedback yet. Somewhere out there, perhaps hidden in a distant or dust-shrouded cluster, there could be an even greater explosion waiting to be found. One that makes Ophiuchus look small by comparison. But for now, Ophiuchus and MS 0735.6 plus 7421 remain the twin giants of cosmic violence, each telling its own version of how the universe handles excess energy. One from the far reaches of space, the other closer to home, both echoing the same truth. that even in the deepest quiet of the cosmos, there are moments when gravity itself loses its restraint. Between these two titans, astronomers have found a key to understanding how energy shapes the universe on its grandest scales. And as they continue to observe them, they are, in essence, listening to the universe tell the same story twice, each time in a different voice. The hidden engines of the universe. An active galactic nucleus forms when a supermassive black hole begins devouring gas, dust, and even entire stars that drift too close. As this material spirals inward, it doesn't fall directly into the black hole. Instead, it forms a spinning accretion disk. The result is a blazing inferno of radiation that can stretch across the electromagnetic spectrum, with some of the energy escaping in the form of colossal jets. These AGN come in many varieties: quasars, blazars, Seyfert galaxies, radio galaxies. But they are all different expressions of the same underlying process, a black hole converting matter into energy with an efficiency unmatched by anything else in nature. When astronomers observe a quasar, for example, they are witnessing an AGN in its most luminous form. Quasars are so bright that they can be seen from billions of light-years away, meaning that some of the ones we detect today shone when the universe was less than a tenth of its current age. To look at them is to see the early universe in a state of feverish activity, with galaxies growing and black holes feeding voraciously. Without them, galaxies might continue forming stars unchecked, consuming all their available gas in a few billion years and burning out early. With them, the universe achieves a kind of equilibrium. The energy that AGN inject into their surroundings prevents galaxies from collapsing under their own gravity. It may even explain why the largest galaxies seem to stop growing after a certain size. Their own central black holes keep them in check. Observations have revealed that these AGN are not rare events. Nearly every massive galaxy appears to go through an active phase at some point in its life, especially in the early universe. Back then, mergers between young galaxies were common, funneling gas towards their centers and igniting bursts of black hole feeding. During these episodes, the energy released could easily rival that of an entire galaxy cluster. It's estimated that in some quasars, up to 10% of the rest mass energy of infalling matter, as described by E equals mc squared, is converted into radiation. By comparison, a nuclear explosion on Earth releases only about 1/1000th of that fraction. The sheer scale of these processes means they influence not only individual galaxies, but the evolution of the universe as a whole. The radiation and winds from AGN enrich intergalactic space with elements forged in earlier generations of stars. They stir and heat the cosmic medium, affecting how matter collapses into new structures. The jets emitted by some AGN are among the most extraordinary features in the universe. Within these jets, particles are accelerated to energies far beyond what any human-made accelerator can achieve. They may even be responsible for some of the mysterious cosmic rays that bombard Earth. At smaller scales, AGN can alter the fate of entire galactic disks. In some galaxies, astronomers have observed winds so strong that they blow out the central regions entirely, cutting off the supply of cold gas needed for star formation. In others, the opposite happens. The compression from AGN-driven shocks triggers new waves of starbirth, creating bright rings of young, hot stars around the nucleus. This duality makes AGN one of the most intriguing features of cosmic evolution. They are unpredictable, sometimes nurturing, sometimes devastating, but always central to how galaxies live and die. One of the most mysterious aspects of AGN is their variability. Some quasars flicker on timescales of days or weeks, their brightness changing unpredictably. Others can shut off almost entirely, going dormant for millions of years before reigniting again. This variability is a direct reflection of the chaotic process of accretion. The feeding patterns of black holes are not steady but bursty, driven by how gas flows inward and how magnetic fields channel it. Some astronomers suspect that this cycle of feeding and starvation might be the norm for galaxies. Most black holes we see today, including the one at the center of the Milky Way, Sagittarius A star, are relatively quiet. But deep down, they may all carry the potential to awaken again under the right conditions. Even though AGN were first discovered through their visible and radio brightness, modern telescopes have revealed their hidden complexity. Infrared observations can see through the dusty veils that often obscure their cores, while X-ray and gamma-ray instruments can trace the most energetic processes near the event horizon. Together, these multi-wavelength studies have painted a picture of AGN as dynamic, multi-layered systems. Surrounding the accretion disk is often a torus, a thick, donut-shaped ring of dust and gas that absorbs and re-emits radiation. Depending on our viewing angle, the torus can either reveal or conceal the central engine, which is why AGN can look so different from one another, even if they are powered by the same mechanisms. Simulations of AGN activity now allow astronomers to model these environments in extraordinary detail. They show how magnetic fields twist around the spinning black hole, how relativistic effects bend light near the event horizon, and how feedback from jets regulates the temperature of surrounding gas. These simulations suggest that black holes act as thermostats for their galaxies, maintaining a balance between cooling and heating that prevents runaway collapse. There's also a growing recognition that AGN played a key role in shaping the early universe. When the first galaxies formed just a few 100 million years after the Big Bang, their central black holes likely grew rapidly, consuming vast amounts of material. The radiation from these early AGN may have helped reionize the universe, stripping electrons from hydrogen atoms and ending the so-called cosmic dark ages. In that sense, the light from black holes helped make the universe transparent again, allowing starlight to travel freely across space. And yet, despite decades of research, the deeper mechanics of these engines remain elusive. Astronomers still debate how the jets are launched, whether they arise purely from magnetic processes or from the rotational energy of the black hole itself. They wonder how accretion disks remain stable under such extreme conditions, and how matter transitions from hot plasma to cold molecular gas as it moves outward. Every new observation seems to add another layer of complexity, revealing that these engines are not simple machines, but living systems, pulsing and evolving across cosmic timescales. When a black hole feeds, the entire galaxy feels it. When it rests, the galaxy cools and quiets. This dance between activity and stillness has shaped the visible universe we see today, from the delicate spiral arms of the Milky Way to the vast cavities carved in distant clusters. Every flicker of an AGN, every outflow of heated gas, is part of an ongoing dialogue between matter and void. And though they are hidden from our eyes, these engines continue to power the cosmic story, unseen but always in motion. When the universe breathes fire, when galaxies flare, when black holes feed, when clusters ignite in waves of energy, the universe is not simply tearing itself apart. It is redistributing its essence. Every cosmic eruption, no matter how cataclysmic it appears, is part of a delicate balance. The eruption that once tore through the Ophiuchus Supercluster, for instance, did not only blast holes in space, it also stirred the invisible gas that fills the cluster, spreading elements and energy over millions of light years. In those superheated clouds were the ashes of countless stars, carbon, oxygen, iron, forged in the hearts of ancient suns and then blown out by supernovas. The explosion mixed these elements into the wider cosmic environment, ensuring that future generations of stars would be born richer in heavy elements than the ones before them. In a way, the colossal blast was an act of cosmic fertilization. This is how the universe evolves. The matter that once belonged to one generation of stars becomes the building material for the next. Without the dispersal of elements from these fiery events, planets like Earth would never have formed. There would be no rocks, no oceans, no living beings capable of wondering where they came from. The violence of the universe is not senseless, it is creative. Energy and matter are constantly exchanged, recycled through events so vast that they stretch the limits of comprehension. When astronomers study galaxy clusters and the cosmic web, They see this process written across the sky. Enormous bubbles, filaments, and cavities trace where energy has moved through space. Competing processes, heating and cooling, suppression and creation, maintain a kind of cosmic equilibrium. The universe is not stable, but it is balanced through cycles of feedback. The hot plasma that fills galaxy clusters and superclusters doesn't cool evenly. When the gas in the central regions begins to radiate away its heat, it can fall inward toward the cluster's heart. That inflow fuels the central black hole, which responds by releasing jets and radiation. The energy from this eruption reheats the gas, halting its inward collapse. Then the cycle begins again. The result is a self-regulating system that can last billions of years. This cosmic feedback is one of the reasons the universe appears stable when viewed on the largest scales, even though its internal processes are anything but calm. Astronomers often compare this process to a kind of cosmic weather system. Instead of air currents, there are flows of gas millions of light years long. Instead of clouds and storms, there are shock waves of plasma rippling through intergalactic space. And at the center of it all are black holes. When their jets ignite, they can create ripples in the surrounding gas, similar to sound waves moving through air. In fact, in the Perseus cluster, astronomers have detected low-frequency pressure waves that are the deepest note ever recorded, a sound 57 octaves below middle C, propagating through a medium tens of millions of degrees hot. The universe quite literally hums with the echoes of its own eruptions. When the universe breathes fire, it also spreads light. Radiation from these eruptions travels across billions of years, carrying information about how matter behaves under extreme conditions. The X-rays emitted from heated gas tell astronomers about the temperature and density of the cluster environment. Radio waves reveal where charged particles spiral along magnetic fields, tracing the paths of long-extinct jets. Even faint optical glows can mark regions where shock waves have compressed gas into glowing filaments. The same way convection mixes the layers of Earth's atmosphere or volcanic activity renews a planet's surface. Black hole outbursts and galactic winds keep the intergalactic medium dynamic. They recycle gas between galaxies and the space between them, distributing metals and maintaining a steady flow of matter. When astronomers model the universe's evolution on computers, they find that including this feedback is essential. Without it, galaxies would grow far too massive and too bright compared to what we actually observe. The most violent forces known to science, cluster-wide explosions, quasars blazing across time, are also the architects of balance. They destroy, but only to rebuild. They heat, but also prevent stagnation. When astronomers look at the remnants of events like the Ophiuchus eruption, they are not just studying wreckage. They are studying the fingerprints of this universal balance. The cavities in the gas, the patterns in X-ray brightness, the faint radio halos that linger for eons. They tell us how much heat was injected, how far it traveled, and how it might influence the next wave of star formation. Each remnant becomes a data point in the grand story of how galaxies evolve, live, and die. Even our own Milky Way participates in this cosmic breathing. At its center lies Sagittarius, a star, relatively quiet by galactic standards, but even it has not always been so calm. Evidence from gamma-ray observations shows that, a few million years ago, it may have unleashed powerful outflows that created enormous lobes of radiation, the so-called Fermi bubbles, extending tens of thousands of light-years above and below the galactic plane. These are miniature versions of the same processes that shape clusters like Ophiuchus. We are not distant observers of these forces. We live within their reach. The distribution of elements in the universe today, from the hydrogen in stars to the carbon in our bodies, owes its existence to countless cycles of cosmic fire. Supernovae forged the first heavy elements. Black holes spread them further. Galaxy collisions mixed them again. Every explosion, every jet, every burst of radiation has contributed to making the cosmos chemically complex. If we could watch the universe over its entire lifetime, compressed into a few minutes, we would see this breathing motion unfold. Galaxies flickering on and off as their black holes feed, jets carving paths through gas, clusters glowing and cooling, then flaring again. The universe would look alive, constantly in motion, a living tapestry of energy exchanges. Though our telescopes capture only snapshots of these immense cycles, each observation brings us closer to understanding how this cosmic respiration sustains everything we know. The universe breathes fire not to destroy itself, but to keep itself alive, to maintain the delicate equilibrium that allows life to emerge in a small corner of space that can one day look back and realize that even chaos, at the grandest scale, has a purpose. The energy scale beyond human comprehension. On Earth, the most powerful explosions ever created by our species are nuclear detonations. The largest of these, the Tsar Bomba, tested by the Soviet Union in 1961, released about 50 megatons of TNT, roughly equivalent to the energy produced by the Sun in a single second. That sounds immense, yet in cosmic terms, it's a spark flickering in a hurricane. Even the Sun, blazing continuously for billions of years, is modest when set against the energy unleashed by some of the universe's titans. Supernovae, the explosive deaths of massive stars, can outshine entire galaxies for a short time, releasing as much energy in a few weeks as the Sun will produce in its entire lifetime. But the Ophiuchus event went further still, crossing into a category that barely seems real. The numbers are difficult to comprehend. Scientists estimate that the outburst from Ophiuchus released around 10 to the power of 54 joules of energy. To put that in perspective, all the energy the Sun emits in its 10 billion year lifetime is about 10 to the power of 44 joules. That means the Ophiuchus eruption released 1 billion times more energy than the Sun will ever produce. If every star in the Milky Way burned for billions of years and combined their output, it still wouldn't come close. The sheer immensity of that number makes it almost meaningless to the human brain. It sits so far above our frame of reference that it becomes abstract, a reminder of how small we truly are within the machinery of the universe. To imagine witnessing such an event is almost impossible. If humanity somehow existed nearby, the eruption would have appeared eternal. It would have been like watching a mountain grow or an ocean freeze, a process too vast for a lifetime to contain. Events like the one in Ophiuchus help expose the limits of human language and perception. When scientists say more energy than all the stars in the Milky Way combined, it's not a metaphor. It's a literal calculation. Yet even hearing it doesn't capture the feeling of it. The human mind evolved to understand campfires and thunderstorms, not jets of plasma traveling through space at relativistic speeds. To truly feel the immensity of these forces requires imagination more than numbers, a willingness to stretch thought beyond familiar boundaries. What's remarkable is that these cosmic eruptions are not rare exceptions. Across the universe, similar events happen continuously, powered by supermassive black holes in countless galaxies. Each one, in its own way, regulates its environment, feeding, burning, and shaping the cosmos. The Ophiuchus explosion stands out because it's so unmistakably enormous that it reminds us of what these engines are capable of. In some sense, the Ophiuchus event forces us to redefine what we think of as violence in the universe. On Earth, an explosion means destruction, an end. In space, it often means transformation. The Ophiuchus blast may have sterilized its surroundings for eons, but the energy it released will echo through the cluster for billions of years, influencing what forms and what doesn't, long after the light of the event fades. The universe's most violent neighbors. As telescopes grow more sensitive and sky surveys become more detailed, astronomers see echoes of violence everywhere. The universe, it turns out, is filled with giants losing their temper. Other galaxy clusters, like Perseus and Hydra A, also bear the scars of colossal black hole outbursts, each one different in detail but similar in spirit. The Perseus cluster is perhaps the most famous of these violent neighbors. Located about 240 million light-years away, it is one of the brightest X-ray sources in the sky. When astronomers turned the Chandra X-ray Observatory toward Perseus, they discovered giant cavities or bubbles carved into the hot gas that fills the cluster. These voids were created by jets of particles blasting outward from the supermassive black hole at the center of the cluster's dominant galaxy, NGC 1275. The energy required to hollow out those bubbles was on the order of hundreds of thousands of supernova, and it wasn't a single burst, but part of a repeating cycle. Each time the black hole became active, it unleashed jets that inflated bubbles, stirred the surrounding gas, and then quieted down, only to awaken again millions of years later. In 2003, scientists using Chandra data discovered pressure waves rippling through the cluster's gas. These ripples had a wavelength of around 30,000 light-years, and their frequency corresponded to a note too deep for human ears to hear, representing the oldest and largest known song in the universe, a faint hum generated by the slow, rhythmic beating of a supermassive black hole. If Perseus is the symphony, then Hydra A is the thunderstorm. Located about 840 million light-years from Earth, the Hydra A cluster holds one of the most dramatic examples of black hole-driven violence ever recorded. At its center lies a galaxy with a supermassive black hole roughly 1 billion times the mass of the Sun. From this core, twin jets of plasma erupt in opposite directions, stretching more than 1 million light-years across. The energy output from Hydra A's black hole is estimated to be more than 10 to the power of 61 ergs of energy, enough to keep an entire cluster of galaxies from cooling for billions of years. Hydra A's outbursts appear episodic, occurring again and again over cosmic time. Radio observations reveal multiple pairs of cavities, each corresponding to a different phase of the black hole's activity. This suggests that the central engine turns on and off in cycles, separated by tens of millions of years. Between each episode, the cluster settles into temporary calm before the next blast reignites the process. Perseus and Hydra A may seem distant and abstract, but they're part of a much larger cosmic pattern. Observations of other clusters, such as MS 0735.6 plus 7421, Hercules A and M87 in the Virgo cluster, reveal similar cavities, jets, and ripples. Each of these systems features a supermassive black hole acting as an engine of transformation. These examples demonstrate that the Ophiuchus event wasn't an isolated anomaly, but the extreme end of a continuum. Across the universe, black holes routinely shape their environments through these immense outflows. The more astronomers study these cosmic neighbors, the more they realize that the universe's violence is structured. Jets from black holes follow magnetic field lines, guiding energy into specific directions. The cavities expand, rise, and displace cooler gas, which then flows back toward the center, feeding the black hole again, a self-sustaining cycle of cause and effect. In Hydra A, the jets stretch far, connecting one system to another across intergalactic space. In Perseus, the ripples of sound waves travel for hundreds of thousands of light-years through an invisible sea of gas. The violence of these black holes echoes through space like a storm spreading across an ocean. Even though we view them from millions of light-years away, the imprints of their power remain vivid. Gamma Ray Burst 2, 21009A, the brightest of all. In October 2022, a burst of light traveled across 2.4 billion light-years of space and finally struck Earth. It was the brightest cosmic explosion ever recorded in human history. Astronomers named it GRB 221009A, though many began calling it by another name, the Boat, short for Brightest of All Time. It arrived unexpectedly. Telescopes around the world began picking up an extraordinary surge of gamma rays, the most energetic form of light known. Satellites that monitor high-energy radiation for cosmic events, including NASA's Fermi Gamma Ray Space Telescope and the Swift Observatory, were suddenly overwhelmed. Instruments designed to handle the most violent known explosions in the universe were flooded with radiation so intense that many of them temporarily went offline. The burst's signal was so powerful that at first, scientists thought something had gone wrong with their detectors. But as observatories across the globe and in orbit confirmed the readings, it became clear that the universe had just sent Earth the brightest gamma-ray burst ever seen. For about 7 minutes, GRB 221009A dominated the high-energy sky. Its brightness exceeded that of every other cosmic source combined. Even though it came from halfway across the universe, if our eyes could see gamma rays, that region of the sky would have appeared to flare like a second sun. Its afterglow, fading slowly over the days that followed, was visible in radio, optical and X-ray light, allowing telescopes on Earth to track its fading brilliance. The initial flash was so strong that it ionized parts of Earth's upper atmosphere, briefly altering how radio waves traveled across the planet. Gamma-ray bursts, like GRB 221009A, are among the most extreme phenomena known to science. They occur when massive stars, dozens of times heavier than the Sun, reach the end of their lives. When their nuclear fuel runs out, their cores collapse under their own gravity, forming a black hole in a matter of seconds. But instead of quietly swallowing the surrounding material, the black hole's birth releases an enormous outpouring of energy. Powerful magnetic fields funnel the collapsing star's material into two narrow jets that shoot outward at nearly the speed of light. When one of those jets happens to point directly at Earth, we witness a gamma-ray burst, a beam of raw energy piercing the universe like a cosmic spotlight. What made GRB 221009A extraordinary wasn't just its brightness, but its rarity. Scientists estimate that an event this powerful might occur only once every 10,000 years, perhaps even longer. The light we saw in 2022 began its journey when multicellular life was still evolving on Earth. For billions of years, it traveled silently through the cosmic dark until it finally met our instruments. To witness such an event in real time is, statistically speaking, almost impossible. Yet it happened, offering astronomers a rare chance to study one of nature's most violent acts up close. When scientists compared the energy of GRB 221009A to the Ophiuchus explosion, they found an intriguing contrast. In terms of total energy released, the Ophiuchus event still reigned supreme. It released as much energy as hundreds of millions of supernovae combined, but it did so slowly, over hundreds of millions of years. GRB 221009A, on the other hand, was much smaller in scale but incomparably faster. All its energy erupted in a matter of seconds. It was like comparing a slow, rolling earthquake that reshapes continents to a lightning strike that splits the sky. Both are powerful, but they operate on entirely different timescales. In that sense, the Ophiuchus eruption and GRB 221009A represent two extremes of cosmic violence. The first is the slow, deep breath of the universe, energy accumulating and releasing across eons as a supermassive black hole rearranges the space around it. The second is a scream, a short-lived but staggering outburst that burns with intensity and then vanishes almost immediately. The black hole at the center of Ophiuchus likely weighed hundreds of millions of solar masses, influencing an entire supercluster of galaxies. The black hole born from GRB 221009A was tiny by comparison, only a few times the mass of the Sun. Yet for those few moments, it was the most dominant source of energy in the cosmos. Astronomers studying GRB 221009A have found that it was unusually close in cosmic terms, meaning just a couple of billion light-years away. Most gamma-ray bursts occur much farther out, often near the edge of the observable universe, their light stretched and dimmed by vast cosmic distances. Because GRB 221009A happened relatively nearby, its light reached us with unprecedented intensity. It provided scientists with a front-row seat to the physics of stellar collapse, to the formation of a black hole at the heart of a dying star, and the creation of relativistic jets that punch through the star's outer layers. The jets themselves are among the most extreme structures in existence. They carry enormous amounts of energy in a narrow beam, moving at 99.999% the speed of light. Inside them, particles are accelerated to incredible energies, producing gamma rays through collisions and magnetic interactions. It's a process that, even today, isn't fully understood. Astronomers believe magnetic fields play a key role, twisting and amplifying, until they focus energy into tight columns that erupt outward with unstoppable force. When one of those columns happens to align with our planet, we see a gamma ray burst. The brightness of GRB 221009A was so intense that it briefly outshone every other gamma ray source in the observable universe combined. For scientists, this provided a unique opportunity to test the limits of their instruments and theories. Even observatories not designed to study gamma rays, like optical telescopes, picked up its afterglow as the blast faded. Some radio telescopes detected echoes of the explosion days later, revealing how the shockwave expanded into surrounding space. From these data, astronomers could reconstruct the size, shape, and speed of the jet, a moving window into one of the universe's most extreme events. In the days after the burst, researchers also observed how its light interacted with the dust in our galaxy. As the X-rays from the explosion traveled through the Milky Way, they scattered off tiny grains of interstellar dust, creating concentric rings of light visible to X-ray telescopes like Chandra. These light echoes were not only beautiful but scientifically valuable, allowing astronomers to map the distribution of dust in our own galaxy. An event billions of light years away taught us something about our own cosmic neighborhood. In Ophiuchus, an ancient and enormous black hole tore through the gas of a galaxy cluster, releasing energy over eons. In GRB 221009A, a newborn black hole was born from a dying star, its jets blazing briefly before fading forever. Both are driven by the same fundamental process, gravity's ability to compress matter into a point of near infinite density, releasing vast amounts of energy in the process. But the contexts are wildly different. These two extremes show just how diverse the universe's engines of destruction can be. Both reveal that the cosmos runs on transformation, stars dying to give birth to black holes erupting to shape galaxies and galaxies, evolving under the influence of these forces. The universe, even in its moments of quiet, is always building, always ready to release the next surge of power. Gamma ray bursts like GRB 221009A act as beacons, cosmic flares that light up the darkness of the early universe. Astronomers use them to probe distant galaxies, to study how matter behaves under extreme conditions, and even to test the laws of physics themselves. Their light carries information about magnetic fields, particle acceleration, and the fabric of space-time. In some cases, gamma ray bursts have revealed the presence of heavy elements forged in stellar collapse, the raw ingredients for planets and life, hypernovas and the death of massive stars. When a massive star nears the end of its life, it faces an inevitable collapse. For millions of years, it has balanced on a razor's edge, its nuclear fusion generating just enough pressure to counteract gravity's pull inward. But once the fusion ceases, that balance shatters. The star's core collapses at unimaginable speed, triggering an explosion so powerful that it can briefly outshine an entire galaxy. This is the birth of a hypernova, the most energetic kind of stellar death known to exist. For a few fleeting moments, the dying star becomes one of the most violent objects in the cosmos. Hypernovas are not just supernovas with a stronger blast. They are the result of extreme physics, of stars that begin their lives with more than 30 or 40 times the mass of the Sun. These giants burn through their nuclear fuel so quickly that they live fast and die young, sometimes lasting only a few million years before collapsing. When the core can no longer support itself, gravity wins completely. The outer layers fall inward, crashing into the dense center and rebounding in a shockwave that tears the star apart. In some cases, the collapsing core forms a black hole, and as surrounding matter spirals inward, it generates twin jets of plasma traveling nearly at the speed of light. These jets burst through the outer layers, blasting into space as gamma ray bursts. The physics driving a hypernova is, in essence, the same process that fuels larger-scale eruptions. It's the same story, just written on a smaller canvas. For astronomers, hypernovas serve as laboratories for cosmic violence. Because they occur more frequently and in greater detail than black hole eruptions in clusters, they allow scientists to study how energy is released, how matter behaves under extreme pressure, and how magnetic fields guide the flow of plasma. Observing a hypernova gives us a glimpse into what happens on the grander scales of the universe, a kind of miniature rehearsal for the cosmic dramas that unfold in places like Ophiuchus. Both shape their surroundings, inject energy into the interstellar or intergalactic medium, and leave behind dense remnants, neutron stars or black holes, that continue to influence the space around them, long after the explosion fades. One of the most famous examples of a hypernova occurred in 1998, known as SN 1998 BW. It was associated with a gamma-ray burst, GRB 980425, marking the first time scientists confirmed a direct link between a gamma-ray burst and a supernova-like event. The explosion was so intense that it challenged existing models of how much energy a single star could release. At its peak, it was tens of times more luminous than an ordinary supernova, suggesting that something extraordinary had taken place deep within, possibly the formation of a black hole at its center. The jets it produced likely tunneled through the outer layers of the star, carrying energy outward and creating the burst that reached Earth. In more recent years, astronomers have found even stronger candidates for hypernovas. Some release as much energy in seconds as our Sun will in 10 billion years. These titanic deaths often produce long-duration gamma-ray bursts, sometimes lasting several minutes, far longer than typical bursts. When these are detected, they often come from distant galaxies, their light traveling billions of years before reaching our telescopes. What we see is not a local event, but a relic from the early universe. A signal from a time when the first generations of massive stars were burning out. The shockwaves from a hypernova spread heavy elements, iron, nickel, gold, into surrounding space. Without these stellar deaths, the universe would be a place of hydrogen and helium, barren and unchanging. Every atom of oxygen we breathe and every speck of iron in our blood was once forged in the heart of a massive star and scattered across the cosmos by an explosion like this. For all their fury, hypernovas are small compared to the energy output of the Ophiuchus eruption. A hypernova might release around 10 to the power of 46 joules of energy, but in both cases, energy comes from the same fundamental process, gravitational collapse, where mass is converted into energy. The same rule that governs the fall of an apple also governs the fall of entire galaxies into the maws of black holes. A hypernova can leave behind a neutron star, spinning hundreds of times per second, or a newly formed black hole. These remnants are themselves engines of energy, emitting radiation and sometimes producing jets of their own. In a way, the star's death is merely the start of another phase in the cosmic cycle. The same can be said for the galaxies at the hearts of clusters like Ophiuchus. Each stage leaves its imprint on the surrounding universe, shaping the cosmic landscape we see today. A hypernova lasts only seconds to minutes, yet its after-effects ripple for thousands of years. And when multiplied across billions of galaxies, these deaths collectively build the structure of the cosmos. The great eruption in Ophiuchus may be grander in scope, but in their final moments these stars demonstrate the same truth. Collisions of giants, black hole mergers. When two black holes collide, the universe itself quivers. Unlike the slow simmering fury of an event like the Ophiuchus eruption, black hole mergers unfold in an instant, an explosive crescendo following eons of silent spiraling. For millions of years, two invisible titans dance around each other, locked in an orbit of doom. With each revolution, they lose energy in the form of gravitational waves, faint ripples in the fabric of space-time. As they draw closer, the orbit tightens, the pace quickens, and the waves grow stronger, until finally, in less than a second, they collide. In that brief moment, they release more energy than all the stars in the observable universe combined. not in light or heat, but in the raw movement of space and time itself. The first time humans detected such an event was in 2015, through the Laser Interferometer Gravitational Wave Observatory, or LIGO. The signal, known as GW150914, lasted just a fraction of a second. It wasn't a flash of light or a burst of radiation. It was a tiny rhythmic stretching and squeezing of the Earth itself. The detectors, each using laser beams to measure minute distortions in distance, recorded a wave that had traveled across more than 1 billion light-years. It was the echo of two black holes, 29 and 36 times the mass of the Sun, colliding and merging into a single larger one. In that collision, roughly 3 solar masses were converted entirely into gravitational energy, an outpouring of power on a scale that had never before been observed. During the peak of such an event, the power output can exceed 10 to the power of 49 watts, greater than all the light emitted by the visible universe. Yet this titanic outburst lasts less than a second. It is the ultimate example of cosmic violence compressed in time, a flash of gravitational energy that travels forever, undiminished by distance or age. To detect it, humanity needed instruments of staggering precision, capable of measuring changes smaller than a proton's width across kilometers. When the first signal was confirmed, it wasn't just a scientific achievement. It was a new sense awakening. For the first time, humanity could hear the universe. But black hole mergers come in many sizes and intensities. Some involve stellar mass black holes, like the ones detected by LIGO. Others, happening in the distant reaches of galaxies, involve supermassive black holes, millions or even billions of times heavier than the Sun. These colossal collisions are thought to occur when galaxies merge, an event that itself takes hundreds of millions of years. As their centers spiral inward, their black holes draw closer together, forming a binary system at the galaxy's heart. When they finally coalesce, they could send gravitational waves rippling across the entire cosmos, so vast in wavelength that only the slow ticking of pulsars, rotating neutron stars that act like cosmic clocks, can reveal them. In 2023, astronomers announced evidence for exactly that, a low-frequency background of gravitational waves detected not by laser interferometers, but through careful timing of dozens of pulsars scattered across the Milky Way. Each pulsar's signal wobbled ever so slightly, as if the space between Earth and the stars was being stretched by unseen waves. These ripples are believed to come from the combined effect of countless supermassive black hole mergers throughout cosmic history, the deep, slow heartbeat of the universe itself. When compared to Ophiuchus, black hole mergers reveal a fascinating contrast in how the universe releases its energy. A black hole merger is instantaneous, a single catastrophic moment of transformation. If the Ophiuchus eruption were a long, roaring inferno, a merger would be a flash of cosmic lightning. The physics of a merger are extraordinary. As two black holes spiral closer, their immense gravity warps the surrounding space-time into a churning vortex. Time itself slows near their event horizons, and the fabric of space becomes so distorted that if one could see it, it would resemble a storm on the surface of a dark ocean. When they finally touch, the merger forms a new, larger black hole that rings like a struck bell. The vibrations, the so-called ring-down phase, are what LIGO and other detectors pick up as the final tones of a cosmic symphony. In that instant, all the complexity of relativity, quantum theory, and cosmic dynamics is distilled into one pure event, matter becoming energy, motion becoming wave. While LIGO detects the quick mergers of stellar mass black holes, the universe may also host far slower, grander collisions between the monsters at galactic centers. Imagine two galaxies colliding, their stars passing harmlessly through each other, while gas clouds compress and ignite in waves of star formation. In their cores, however, their central black holes begin their fatal dance. Over millions of years, they spiral together, losing energy through gravitational waves until they finally merge. The force of this union could send out waves that ripple across billions of light years, subtly warping the very shape of the universe. The energy released in a black hole merger may be brief, but its effects endure. the newly formed black hole can recoil violently, kicked by the asymmetry of the merger's gravitational waves. Some simulations suggest that this kick can be strong enough to eject the black hole from its host galaxy entirely, sending it drifting alone through intergalactic space. If true, then there may be rogue supermassive black holes roaming the cosmos, invisible giants cast out from the galaxies that gave them birth, dragging their accretion disks and faint remnants of starlight behind them. An Ophiuchus-type eruption is like a slow, controlled burn, an engine that runs over epochs. Yet in both cases, gravity is the ultimate fuel. Whether that energy takes the form of light, plasma, or gravitational waves, it is all part of the same cosmic economy. Nothing is wasted. Every explosion, every collision, every burst contributes to the shaping of galaxies, the stirring of intergalactic gas, and the endless rhythm of cosmic evolution. The idea that two objects can orbit one another, shrinking imperceptibly over eons, and then suddenly release energy greater than the output of all the stars in the sky, feels almost paradoxical. Yet that is exactly what happens. The quiet spiral of death ends in a singular instant of fury. What's perhaps most astonishing is that we can now detect and measure these events. Every gravitational wave caught by our instruments represents a story billions of years old. The waves we detect today may have originated when the first galaxies were forming, carrying with them information about black holes that no longer exist in their original form. Through them, the universe whispers its most ancient and violent secrets in the deep, invisible language of space-time. They are the universe's most concentrated form of energy release, where matter ceases to exist as we understand it and becomes pure motion, a wave traveling endlessly outward. The role of dark matter in such events. When we look at the Ophiuchus cluster, what we actually see is only a fraction of what's really there. The visible galaxies, glowing in clusters and filaments, are the most luminous hints of an invisible structure that extends far beyond what light can show. Beneath the radiance of stars and the heat of X-rays lies a vast web of dark matter. In the case of the Ophiuchus Supercluster, dark matter provides the invisible scaffolding around which everything else has formed. Without dark matter, the Ophiuchus cluster wouldn't exist in the form we see today. Its thousands of galaxies would not have gathered together, nor would the massive black hole at its core have been fed with such abundance. Every burst of radiation, every eruption of plasma, every trace of light from that region owes its existence to the quiet gravity of dark matter, shaping the flow of matter across billions of years. Scientists estimate that dark matter makes up about 85% of all matter in the universe. Ordinary matter, the kind that forms stars, planets, and people, accounts for only a small remainder. Yet it is dark matter that acts as the stage upon which cosmic events like the Ophiuchus eruption unfold. Early in the universe, tiny fluctuations in the density of dark matter became seeds for the first structures. Over time, gravity amplified those variations, drawing gas and dust into the densest regions. Galaxies formed there along the invisible filaments of a dark matter network. Eventually, those galaxies merged into clusters and superclusters, each shaped by the hidden gravitational pull of this mysterious material. The Ophiuchus Supercluster sits at one of these intersections, a gravitational knot where dark matter has pooled for billions of years. Though we can't observe it directly, its presence is mapped through the way galaxies move and how light bends as it travels through space. In Ophiuchus, the gravitational lensing data suggests a massive halo of dark matter enveloping the entire structure, far outweighing all the stars and gas combined. It is this halo that holds the cluster together, preventing it from flying apart under the immense energy released by its central explosion. Without the stabilizing presence of dark matter, the Ophiuchus eruption might have torn its surroundings to pieces. The black hole's jets and radiation could have blown the cluster's gas away entirely. But the deep gravitational well of dark matter acted as a cosmic anchor. It kept the system bound, even as unimaginable forces tore through it. Astronomers studying Ophiuchus and other clusters have noticed that the hot gas filling these environments tends to trace the same shapes as the underlying dark matter halos. The gas settles into the gravitational valleys carved by dark matter, forming vast, glowing reservoirs that emit X-rays. When a black hole at the cluster's center erupts, the shock waves and jets it releases expand through this gas, following the contours of the invisible framework beneath. Even though dark matter doesn't interact with radiation or plasma directly, it defines the geometry of how the energy spreads, guiding the cosmic storm like the unseen walls of a canyon shaping the path of wind. To visualize this, imagine a river of light and gas flowing through an invisible landscape. The water doesn't know the shape of the valley it's running through, yet every bend, every rapid, every eddy is determined by the ground beneath it. In the same way, dark matter sculpts the motion of gas and stars without ever revealing its own form. In Ophiuchus, the explosion's shockwave expanded outward not randomly, but in patterns that echoed the underlying dark matter distribution. Some regions offered resistance, others allowed the energy to flow freely, creating the asymmetric cavity we now see in X-rays. The role of dark matter extends beyond shaping structure. It may also control timing. In regions with dense dark matter, gas tends to accumulate more efficiently. This provides the raw fuel that eventually falls into supermassive black holes, triggering eruptions like the one seen in Ophiuchus. Conversely, in areas with weaker dark matter density, less gas is available, and galaxies evolve more quietly. This means that the frequency and power of such cosmic explosions could depend heavily on how dark matter is distributed across the universe. Clusters rich in dark matter halos are, in a sense, more fertile grounds for extreme events. The idea that something we cannot see governs such monumental forces has reshaped modern cosmology. When astronomers simulate the evolution of the universe, they begin not with galaxies, but with dark matter. Computer models start as nearly uniform clouds of invisible particles. Gravity then amplifies tiny irregularities in their distribution, causing the dark matter to clump together. These clumps grow into filaments and nodes, the backbone of the cosmic web. Only after this hidden skeleton forms does normal matter follow, condensing into the luminous galaxies we observe today. The Ophiuchus cluster, with its immense scale and complex structure, is one of the finest examples of how this hidden architecture gives rise to the visible universe. There is also growing evidence that dark matter influences how energy behaves on large scales. When the Ophiuchus black hole erupted, the jets it produced traveled through a medium shaped by dark matter's gravity. The density of the gas, its temperature, and its ability to absorb or deflect energy were all determined by how the invisible mass was distributed. This may explain why the explosion carved a cavity of such specific shape and size. The event's outcome wasn't simply a product of the black hole's power, but of the environment it existed in, an environment designed by dark matter over cosmic time. Some researchers even speculate that dark matter could indirectly regulate the life cycles of galaxies. By controlling how gas flows and where it gathers, it determines how often black holes can feed. A cluster with dense dark matter may experience repeated cycles of violent eruptions as gravity continually channels new material toward the center. In this sense, dark matter acts as both the foundation and the fuel distributor of the cosmic engine. Despite its importance, dark matter remains one of science's greatest mysteries. Countless experiments have searched for the particles that might make it up, from underground detectors waiting for rare collisions to space telescopes, scanning for faint signals of decay. But none have yet succeeded. We know it's there because of its gravitational pull, but we don't know what it is. It could be composed of exotic particles beyond the standard model of physics, or it could arise from an entirely new understanding of gravity itself. Whatever its nature, its presence is undeniable. The Ophiuchus Supercluster, like all great structures in the cosmos, is a monument to its quiet influence. Even as astronomers continue to unravel the physics of the Ophiuchus explosion, they understand that they are only reading one layer of a much deeper story. Beneath the radiance lies the true structure of the universe. Without it, there would be no galaxies, no stars, no eruptions, and no universe as we know it. Dark matter doesn't just fill space, it defines it. It is the unseen architect behind every burst of light and every cosmic storm, shaping the universe through gravity. The challenges of studying the distant past. When we look at the Ophiuchus Supercluster, we are seeing it as it was nearly 400 million years ago. The light and radiation coming from that region have spent nearly 500 million years crossing the cosmic ocean to reach us. This time, delay is one of astronomy's greatest gifts, and also one of its greatest challenges. It allows scientists to witness history unfolding on a scale that no human timeline could ever contain. Yet it also traps us in a strange perspective, where everything we observe has already happened, often millions or billions of years ago. Astronomers often say that looking deeper into space is like looking deeper into time. When telescopes capture distant galaxies, they are recording moments from the cosmic past. A galaxy seen 1 billion light-years away shows us what it looked like 1 billion years ago. This means that the universe we study is layered not just across space, but across time itself. In one image, an astronomer might see galaxies in all stages of evolution, some just forming their first stars, others long past their prime, and a few already consumed by mergers or black holes. It's a vast, simultaneous timeline, stretched across billions of light-years, frozen in light. The difficulty comes when scientists try to piece these fragments into a coherent story. They can't simply observe how the Ophiuchus cluster changed over time. They can only compare it to other clusters at different distances and infer what must have happened in between. When studying something as immense and ancient as the Ophiuchus eruption, every photon counts. The radiation that reaches us has been traveling through intergalactic space for hundreds of millions of years. Along the way, it has been stretched, bent, and sometimes scattered by intervening matter. Dust and gas can absorb parts of the signal. Gravitational fields can distort its path. By the time it reaches our instruments, it's faint, a whisper of what was once a roar. Astronomers must reconstruct the event from this faint residue, correcting for every distortion along the journey. The X-rays emitted by the hot gas around the Ophiuchus cluster have lost some of their energy due to the expansion of the universe, a process known as redshift. The same thing happens with visible light from distant galaxies, shifting them toward the red end of the spectrum. This means that to study these events properly, astronomers must translate what they detect into what was originally emitted, a process that requires precise models of cosmic expansion. Even a small miscalculation in redshift can change the estimated distance, and therefore the estimated age of what they're observing. The time delay also complicates how we interpret cause and effect in cosmic events. By the time we detect the aftermath, the environment around it may have already evolved beyond recognition. The galaxies that once surrounded a blast might have moved, merged, or faded. Astronomers can only guess what the cluster looks like now, whether it has settled back into equilibrium, or if new eruptions have already reshaped it again. This limitation forces scientists to become historians of the universe, reconstructing events with the tools of forensics and theory. They analyze clues and build models of how the event unfolded over time. Then they run computer simulations that recreate the explosion, frame by frame, to test whether it matches what we see. It's not unlike an archaeologist rebuilding a collapsed temple from scattered stones, trying to imagine the structure as it once stood. Another challenge is the sheer faintness of ancient light. The further away something is, the weaker its signal becomes, spreading out across larger areas of space as it travels. Detecting those faint photons requires sensitive instruments and long exposure times. Some observations of clusters like Ophiuchus can take hundreds of hours of telescope time to collect enough data for a clear picture. Even then, the result isn't a crisp photograph, but a blurred map of radiation intensity that must be carefully interpreted. The delay also means that any changes happening in the cluster now, new star formations, black hole activity or mergers, won't be visible to us for another 400 million years. We are forever separated from the present of distant galaxies. To understand what's happening there now is impossible in any direct sense. We can only predict it based on physical laws and patterns we observe elsewhere. The irony is that while we can see billions of years into the past, we will never see the present universe in its entirety. This distance-time paradox means that our cosmic picture is inherently incomplete, a snapshot of an evolving universe seen in layers of delay. The Ophiuchus eruption, colossal and ancient, was a chapter written in the universe long ago. Yet, despite this immense gap in time, we can still understand it with precision. Through the combination of telescopes and low-frequency radio arrays, scientists can estimate the age, temperature, and structure of the gases with remarkable accuracy. They can calculate how fast the shockwaves moved, how much material was displaced, and even when the central black hole likely went dormant. It's an astonishing achievement. Deciphering a billion-year-old event using signals that have traveled across the expanding universe like bottles cast into a cosmic sea. By observing many clusters at different distances, and therefore different ages, they can piece together how such systems grow and interact over time. Some clusters are young, still forming from the merger of smaller groups. Others, like Ophiuchus, are mature, massive, and stable, though occasionally shaken by cataclysmic events. The fact that we can study these various stages across cosmic time gives us something we can't obtain any other way, a window into the universe's own history of formation and change. Still, the delay remains a barrier we cannot cross. No matter how advanced our telescopes become, light will always take time to travel. We can never see the universe as it is, only as it was. The Ophiuchus Supercluster may have already changed completely since the eruption we now study. Its black hole might be quiet again, its gas redistributed, its cavity refilled. But we won't know for hundreds of millions of years. That realization adds a layer of poignancy to astronomy. It's a science that demands patience and imagination. Patience to collect the faintest signals from the distant past, and imagination to picture what those places might look like today. Every time an astronomer looks at it through a telescope, they are engaging in a kind of time travel, witnessing the echo of an ancient event that shaped the universe we now inhabit. Each observation is a bridge between eras, connecting a violent moment in the depths of space to a quiet, curious civilization on a small blue planet. The first to look back and realize just how far the light has traveled. Why the universe still surprises us. Even when astronomers believe they've mapped out the rules, the cosmos finds a way to bend or break them. For instance, when black holes were first theorized, few believed they could ever be directly observed. When the first one was imaged decades later, it didn't just confirm theory, it transformed how we thought about light, gravity, and space itself. The same thing happened with fast radio bursts, those mysterious flashes that last milliseconds yet release more energy than our sun emits in days. They seemed impossible until they were found. And now they're part of the ever-growing puzzle of the universe's behavior. Moments like this show how science grows not from certainty, but from curiosity. Each time something unexpected is found, it forces a re-evaluation of what's known. Astronomers revise equations, run new simulations, and sometimes even abandon old theories entirely. It's a process that's both humbling and exhilarating. The universe doesn't care about human expectations. It simply is. It behaves according to its own laws, and it's up to humans to keep catching up. And catching up isn't easy. The cosmos often hides its most extraordinary behavior behind layers of distance and obscurity. Detecting faint signatures across that gulf of time is like listening for a whisper in a hurricane. But when that whisper is finally heard, when it's confirmed and understood, the implications ripple through all of science. One of the reasons the universe still surprises us is that we can only observe a fraction of it. Most of its matter and energy remain invisible, detectable only through their gravitational influence or subtle distortions in light. Dark matter and dark energy together make up about 95% of the cosmos, yet their nature remains a mystery. It's entirely possible that some of the strangest events astronomers detect, like the Ophiuchus explosion, are shaped by these unseen forces. The visible universe may just be the surface of something much deeper. Every observation is like seeing the shadows cast by a hidden architecture, hinting at structures that are still beyond our reach. Another reason for continual surprise is that the tools used to explore the universe are always evolving. A few decades ago, telescopes were limited to visible light. Now, astronomers can observe in X-ray, gamma-ray, radio, and infrared wavelengths, each revealing a different layer of reality. What appears empty in optical light can blaze with energy in X-rays. A dim patch of sky can turn out to be a hub of furious star formation when seen in infrared. The universe is not uniform. It changes appearance entirely, depending on how you look at it. This multi-wavelength view has uncovered phenomena that no one even knew to search for. But beyond instruments and technology, there's something deeper at work, the element of human imagination. Each discovery opens new doors because someone dared to question the familiar. When the Ophiuchus data looked odd, it would have been easy to dismiss it as an error. Yet scientists persisted. They compared, recalibrated, and theorized until the impossible began to make sense. This blend of skepticism and wonder is what drives science forward. The cosmos continually tests human assumptions, and in doing so, it refines the way humanity understands its place in the universe. Every surprise also has a ripple effect. When something as immense as the Ophiuchus eruption is found, it doesn't just change how we see that one cluster, it affects how we interpret all similar systems. Astronomers start re-examining older data, wondering what other signals they might have overlooked. Were there faint cavities or temperature gradients that now, in hindsight, point to smaller versions of the same phenomenon? Science is often built on reinterpreting the past through the lens of the present. Each revelation acts like a key that unlocks older mysteries. Even the idea of what counts as a discovery keeps evolving. Sometimes it's not about finding a new object or event, but about realizing that familiar ones behave in unfamiliar ways. For instance, the early models of galaxy clusters suggested that most of their heat and motion came from the gravitational pull of dark matter. But discoveries like Ophiuchus showed that energy from supermassive black holes could dramatically reshape these environments, heating and moving gas across millions of light years. It wasn't a new type of object, it was a new kind of understanding. Perhaps the greatest surprise of all is how much remains undiscovered. Despite the incredible achievements of telescopes and space observatories, humans have only mapped a small portion of the observable universe. There are billions of galaxies, each with its own history of collisions, explosions, and eruptions. Somewhere out there, there may be clusters even more extreme than Ophiuchus, or events that don't fit any current model at all. The cosmos is vast enough that even the rarest phenomena are happening somewhere, right now. Astronomy's constant surprises also serve as a mirror for human limitations. Each time scientists think they've reached a complete understanding, nature proves otherwise. The expansion of the universe, once thought to be slowing down, turned out to be accelerating. The center of our galaxy, once assumed to be calm, hosts a ravenous black hole. Even the definition of what constitutes a planet had to change after discoveries of exoplanets shattered old rules. The cosmos does not fit neatly into human categories. It forces those categories to evolve. And yet, this unpredictability is what makes the journey worthwhile. The surprises are not failures of science. They're signs of progress. They mean we're reaching the boundaries of knowledge and pushing beyond them. The Ophiuchus cluster is just one example in a long lineage of discoveries that forced scientists to think bigger, to reimagine the scale of cosmic power. Ultimately, the universe surprises us because it's alive in a way that data alone can't capture. Not alive in the biological sense, but in its dynamism, its constant motion and change. Galaxies collide, stars are born and die, black holes feed and flare, and clusters evolve over billions of years. As instruments grow sharper and minds grow more curious, the universe will keep revealing itself, one mystery at a time, one surprise after another. Could it happen again? Could an event like the Ophiuchus explosion happen again? Astronomers believe the answer is yes, but with a crucial caveat. Such colossal eruptions are among the rarest phenomena in the cosmos. They require a perfect storm of conditions, a supermassive black hole at the center of a galaxy cluster, surrounded by enormous reservoirs of gas and a buildup of energy that, for reasons still not entirely understood, releases all at once. But given the sheer number of galaxies in the universe, hundreds of billions, each with its own central black hole, it's almost certain that somewhere, at this very moment, something just as powerful is unfolding beyond our reach. To look for the next one, scientists turn their attention to the hearts of other galaxy clusters. These regions are often dominated by massive elliptical galaxies with black holes, billions of times the mass of the Sun. Normally, these black holes feed quietly, drawing in gas that spirals toward the event horizon, heating as it falls. But every so often, that calm feeding process becomes unstable. Magnetic fields twist, accretion disks warp, and jets of plasma are expelled at near light speed. If the outburst grows large enough, it can blow away the gas filling the cluster's central cavity, leaving signs that an eruption has taken place. Astronomers have seen smaller versions of these cavities in other clusters before. Ophiuchus simply pushed this phenomenon to its limit. The next great event may already be brewing in another cluster, its signals still traveling across cosmic distances toward us. Detecting such eruptions isn't straightforward. That's why astronomers rely on long-term monitoring, comparing images taken years or even decades apart. Subtle shifts in temperature, changes in the distribution of X-rays, or newly formed radio lobes can hint at brewing activity. Each cluster is like a volcano under watch, mostly dormant, but never entirely at rest. It's possible that the next colossal explosion might not come from a cluster we already know. Many of the largest galaxy clusters remain hidden behind the thick dust of the Milky Way, or too distant for current instruments to resolve in detail. Future telescopes, like the upcoming Lynx X-ray Observatory or the Square Kilometre Array, could uncover them, peering farther and with more sensitivity than anything before. Each new generation of instruments extends the horizon of discovery, increasing the odds of witnessing something as extreme as Ophiuchus again. Astronomers build models to predict what the early signs of such an eruption would look like. Before the explosion itself, a black hole's accretion disk may show changes in brightness or temperature. Its jets might flicker or bend as they fight against surrounding gas. Ripples could begin forming in the hot plasma of the cluster's core, a kind of pressure wave that, given enough time, might expand into the enormous cavity seen in Ophiuchus. Each observation is a potential clue, a hint of what might come next. To identify potential candidates for such events, scientists study clusters with signs of unusual energy imbalance. When the hot gas in a cluster appears too uniform, it might mean that the central black hole hasn't been active for a long time, storing up energy that could one day erupt. Other times, astronomers spot asymmetric patterns, where one side of the cluster seems hotter or more diffuse than the other. That's often a hint that something has already begun to stir. These subtle signs are what make the difference between a calm cluster and one on the verge of awakening. Using supercomputers, astrophysicists model clusters over billions of years, allowing them to see how small fluctuations can lead to massive outbursts. These simulations show that a single event can release enough energy to disrupt an entire cluster for hundreds of millions of years. They also reveal that once a black hole has erupted on such a scale, it may enter a long dormant phase. The Ophiuchus explosion may not have been its first, nor its last. Observations of the Hydra A cluster and the MS 0735+74 system show massive cavities similar in structure to those in Ophiuchus, though smaller in scale. These are the early candidates for events of comparable magnitude, snapshots of the same phenomenon in different stages of evolution. Each one offers another clue about how often these titanic releases occur and how they shape the cosmic landscape. There's also the intriguing thought that the next great eruption might already be known, just not yet recognized for what it is. Data archives hold years of observations from hundreds of clusters, many of which have never been fully analyzed. Somewhere in that data could be the faint signature of another giant cavity, or the ghostly trail of a jet millions of light years long. The challenge is finding it amid the noise, a task that now increasingly involves artificial intelligence. Machine learning algorithms are being trained to spot subtle patterns that human eyes might miss, scanning through terabytes of data to flag potential candidates for further study. The universe moves slowly, but the tools we build to observe it move faster each year. Every improvement in sensitivity, resolution, or wavelength coverage increases the odds of catching one of these cosmic giants in the act. Perhaps one day, astronomers will witness the early stages of such an eruption, a moment when a black hole's jets begin to expand outward, heating the surrounding gas, setting off ripples that will echo through space for millions of years. Until that day, the search continues. Somewhere in the darkness, beyond the reach of current telescopes, another cluster may already be stirring, its black hole gathering power. And though its light will take eons to reach us, the event itself is already written into the fabric of the cosmos. When that light finally arrives, the story of Ophiuchus will begin again, in another place, another time. Could humanity ever create an explosion so large? The universe operates on energy scales so vast they almost seem designed to remind us of our limits. But could that ever change? Could a civilization, human or otherwise, ever create an explosion so powerful it rivals a supernova or a black hole's eruption? Our most powerful engines today rely on the conversion of matter into energy through nuclear reactions. Fission, the splitting of heavy atoms like uranium or plutonium, is relatively inefficient. Only about 1% of the atom's mass becomes energy. Fusion, the process that powers the sun, is far better, as it releases about 4 times more energy per unit of mass than fission. If humans could control fusion at scale, we could harness staggering amounts of power, but even then it's a mere whisper compared to the universe's grander fireworks. A typical supernova converts about 1/10 of a solar mass into energy. That's roughly 2 times 10 to the power of 44 joules, an energy output millions of trillions of times greater than all nuclear weapons ever detonated combined. And that's just the starting point. Hypernovae, collapsars, and gamma-ray bursts push those limits even further. Yet the Ophiuchus explosion dwarfs them all by orders of magnitude again. To even imagine humans recreating that scale feels absurd. And yet, it opens the door to fascinating speculation about what might one day be possible. If the key to such power is mass-to-energy conversion, then theoretically there's one ultimate mechanism: annihilation. When matter and antimatter meet, they destroy each other completely, turning 100% of their combined mass into energy. No other known process is so efficient. Just 1 kilogram of antimatter colliding with 1 kilogram of matter releases about 1.8 multiplied by 10 to the power of 17 joules, the equivalent of 43 megatons of TNT, close to a Tsar bomber. In principle, if you had a few trillion tons of antimatter, you could mimic the energy release of a small star. But therein lies the problem. Creating and storing antimatter is almost impossibly difficult. Right now, all of humanity's particle accelerators combined have produced only a few nanograms of antimatter, and even that tiny quantity requires immense energy to create, more than you'd ever get back by annihilating it. The process is so inefficient that building a bomb or reactor from antimatter would cost more energy than it could ever release. On top of that, Antimatter can't touch normal matter without immediate annihilation, meaning it must be suspended magnetically in vacuum chambers. Any containment failure would trigger an explosion, albeit still minuscule compared to cosmic scales. Even if, by some miracle, we discovered a way to manufacture and store antimatter efficiently, the total energy required to reach supernova levels would be unfathomable. To match the energy of a typical supernova, you'd need to annihilate roughly 10 to the power of 27 kilograms of matter and antimatter, comparable to the entire mass of Jupiter. Humanity has never handled more than a few kilograms of nuclear fuel in a single device. The gulf between those two numbers is not just large, it's almost meaningless. It's like comparing the energy of a matchstick to the sun. That's not to say humans will never harness greater forces. Over the next centuries, our energy technologies could evolve far beyond fusion or antimatter. Concepts like Dyson spheres, massive structures that capture the energy output of an entire star, or black hole power plants have been seriously proposed by physicists. A sufficiently advanced civilization could, in theory, focus or redirect stellar or gravitational energy on colossal scales. Some have speculated that a Type 2 or Type 3 civilization on the Kardashev scale might be able to trigger artificial stellar collapses or black hole events, deliberately setting off explosions as powerful as the ones we observe in deep space. But even if the engineering were possible, there's an ethical and existential barrier. Why would any civilization create such destruction? Cosmic explosions like the one in Ophiuchus don't merely burn bright. They sterilize entire regions of space, erasing planets, atmospheres, and potential biospheres. A deliberate act of that scale would border on cosmic suicide. Perhaps as civilizations advance, they grow more cautious, not more destructive. The universe itself demonstrates how easy it is to lose stability. Stars live on a balance between pressure and gravity. Disrupt that balance and everything collapses or explodes. Advanced beings might learn to value equilibrium over spectacle. Maybe the comparison shouldn't be about total energy, but about relative control. In that sense, humanity already wields godlike precision. We can release energy atom by atom, shape magnetic fields, and manipulate particles that once existed only in theory. The scale may be small, but the mastery is enormous. The universe, for all its grandeur, operates blindly. It doesn't choose to explode. Humans, on the other hand, can design, plan, and foresee outcomes. Our creations, fusion reactors, particle colliders, laser arrays, are miniature echoes of cosmic processes, controlled rather than chaotic. Take the National Ignition Facility in California, for example. It uses 192 high-powered lasers to compress a tiny fuel pellet to millions of degrees, briefly replicating the conditions at the heart of a star. Each experiment releases a burst of energy lasting billionths of a second. Yet for that instant, it creates a controlled fusion event similar to those inside the Sun. It's a glimpse of stellar power contained in a lab. Not to destroy, but to understand. In that sense, humanity may never match the energy output of the cosmos, but it can match its creativity. Another frontier might lie in manipulating space-time itself. Theoretically, a civilization could tap into vacuum energy, the zero-point fluctuations of quantum fields that exist everywhere. The total vacuum energy of the observable universe is immense, but extracting it remains purely speculative. Some models suggest that if vacuum energy could ever be harnessed or destabilized, the result would be catastrophic, a false vacuum decay, where the universe's underlying quantum state collapses, releasing energy across the cosmos and rewriting the laws of physics themselves. It's the ultimate forbidden experiment, one that scientists agree is best left to thought experiments. The more we learn about energy, the more we realize that true cosmic power comes not from explosions, but from balance. Stars explode because they can no longer contain themselves. Galaxies erupt when their centers lose equilibrium. Even black holes, those ultimate engines of energy, feed in silence for eons before releasing a fraction of their power in violent jets. The most advanced civilizations, if they exist, may have learned to avoid these extremes, channeling energy smoothly rather than violently. Humanity's path may follow a similar pattern. Rather than building bombs larger than stars, we may instead become experts at managing stellar and planetary resources, constructing vast, stable networks of energy, transforming our solar system into an intricate machine that runs indefinitely. We might never match the flash of a cosmic explosion, but we could achieve something the universe rarely sustains: enduring order. Even so, there's an emotional pull in imagining it, a human-made eruption visible across galaxies, a deliberate flare to announce that intelligent life had mastered the ultimate force. We build because we wonder what could be built. We calculate because we want to know what's possible. Maybe that's the point. We don't need to rival the cosmos to be part of its story. The fact that we can even comprehend these energies, that our minds can model them, name them, imagine recreating them, is already a kind of cosmic power in itself. The Kardashev scale and the power of civilizations. When astronomer Nikolai Kardashev first proposed his scale in 1964, he wanted a way to categorize civilizations based on how much energy they could harness, because in theory, the power available to a civilization directly determined the strength of the signals it could send across the stars. A weak civilization might only broadcast as far as its own planet. A more advanced one could beam signals across entire galaxies. It was a simple, elegant idea. Yet it has become one of the most enduring frameworks for thinking about the ultimate limits of intelligence and power in the cosmos. Kardashev divided civilizations into three broad types. A Type 1 civilization could use all the energy available on its home planet. Type 2 could harness the energy output of its entire star. And Type 3 could command the energy of an entire galaxy. On paper, it was a straightforward progression. In practice, it describes a leap from our current capabilities to godlike control over the forces of nature. Humanity, by Kardashev's measure, doesn't even register as a full Type 1 yet. We're somewhere around 0.73 on the scale, capable of using about a few millionths of the total energy Earth receives from the Sun. That's enough to reshape landscapes and reach orbit, but not nearly enough to influence the destiny of worlds. It shows how far we've come and how small we still are. Imagine a Type 2 civilization, one capable of capturing all the energy of its parent star. To do this, it might build a Dyson sphere or a swarm of orbiting satellites that completely encompass its sun, absorbing every ray of light and redirecting it for use. The engineering alone is almost beyond comprehension. Billions of platforms orbiting in perfect synchronization, built from the raw material of entire planets. But if such a project were possible, it would produce a civilization powered by 10 billion times the energy humanity currently consumes. Now imagine going further. A Type 3 civilization operating on the scale of galaxies would have mastery over not just stars, but black holes. It could harvest the rotational energy of spinning black holes using mechanisms like the Penrose process, drawing power from the warping of space-time itself. It could rearrange stellar populations, move planets between systems, or even engineer artificial explosions to clear galactic cores. In other words, it could do things on the scale of the Ophiuchus event, not accidentally, but deliberately. The explosion in the Ophiuchus Supercluster released more energy than hundreds of millions of supernovas combined. To even comprehend what kind of civilization could control or cause such an event, one must imagine beings far beyond Type 3, perhaps Type 4 or beyond, capable of manipulating entire clusters of galaxies. These levels weren't part of Kardashev's original model, but later, thinkers have extended the scale. A Type 4 civilization might harness the energy of an entire universe, while a Type 5 could command the multiverse itself, should it exist. At that point, the distinction between civilization and cosmic law begins to blur. Still, the scale remains a valuable thought experiment because it connects two ideas: power and intention. To release an Ophiuchus-level explosion intentionally, a civilization would need not only unimaginable energy, but also a reason to use it. What purpose could justify unleashing that kind of force? Perhaps it's a method of galactic engineering, reshaping space to prevent collisions between clusters. Perhaps it's a byproduct of a failed experiment involving black holes or vacuum energy. Or maybe, from their perspective, it's not an explosion at all, but a controlled event, like turning on a cosmic engine. From our human vantage point, it's difficult to imagine such control. Our own energy systems are fragile and limited. We rely on chemical combustion for most of our transportation, nuclear fission for part of our electricity and sunlight, only in a modest fraction. We spend enormous effort extracting, burning and transmitting energy just to power lights and screens. To reach even Type 1 status, we'd need to capture every joule Earth receives from the Sun, about 1.7 times 10 to the power of 17 watts, and use it efficiently without destroying our environment. That requires global coordination, advanced technology, and sustainable balance, none of which we have fully achieved. But the Kardashev scale encourages looking upward. Type 2 civilizations might use solar engineering, capturing and redistributing stellar output with the precision of celestial architects. Type 3 civilizations might use gravitational manipulation, harnessing energy directly from black holes or dark matter fields. They would not rely on fossil fuels or nuclear reactors. They would manipulate the fundamental forces of physics. If an Ophiuchus-level explosion were ever artificially triggered, it might be because such a civilization decided to use black hole jets as a means of moving matter across intergalactic distances, or perhaps as a form of cosmic communication. To put that into perspective, the energy released in the Ophiuchus event is roughly the total energy our Sun will emit over 10 trillion years. If a civilization could tap into that much power, it could remake the fabric of its galaxy. It could light up dark regions of space, move clusters of stars, or even control the expansion of the universe itself. And yet, there's no evidence that such civilizations exist, or at least none we can detect. That silence leads to one of the great paradoxes of cosmic thought. If it's physically possible to reach these scales, why haven't we seen anyone doing it? Perhaps the answer lies in efficiency. Advanced civilizations might not waste energy in grand explosive gestures. They might have evolved toward minimalism, achieving more by using less. They could exist in quiet equilibrium, operating below our detection thresholds. The Kardashev scale, while useful, measures only one thing: energy consumption. But intelligence might not scale linearly with power. A truly advanced civilization might find ways to manipulate information or quantum fields without vast energy expenditure. From their point of view, the Ophiuchus explosion could be seen not as a sign of sophistication, but of chaos, the kind of uncontrolled release they long ago learned to avoid. Still, it's fascinating to think about how humanity fits into this cosmic hierarchy. We are a young species, barely beginning to harness the power of our own planet. Yet our minds have already conceived of ideas that stretch beyond galaxies. Every time we build a more efficient reactor, launch a solar probe, or simulate the behavior of black holes, we inch a little closer to understanding what it means to advance along the Kardashev scale. It might take centuries, even millennia, but the direction is clear. Energy defines potential, and potential defines destiny. In the meantime, the scale serves as a kind of cosmic roadmap. It shows where we might go if we survive long enough to continue climbing. Type 1 marks planetary unity, mastering weather, oceans and resources without collapse. Type 2 marks stellar mastery, building structures in orbit, redirecting solar winds, mining asteroids. Type 3 marks galactic engineering, commanding the birth and death of stars. Beyond that, the imagination stretches into the unknown. What does Type 4 look like? Perhaps it's not a civilization at all, but a kind of distributed intelligence, woven through space-time itself. And that brings us back to the Ophiuchus explosion. If something out there could trigger an event of that scale, it either possessed unimaginable power or stumbled into catastrophe. In both cases, It fits perfectly within the Kardashev framework. The scale doesn't just measure energy, it measures consequences. To wield that much force means taking responsibility for cosmic environments, for the life and matter that depend on them. Whether natural or artificial, every explosion leaves an imprint, a story of power and its limits. For now, humanity is still learning how to manage its first steps. Our lights shine faintly compared to the glow of a single star, but our curiosity reaches much further. The Kardashev scale tells us that the journey to power is also a journey to understanding. To grasp the kind of energies that shape clusters and galaxies, we must first learn to balance the ones that power our own civilization. In that sense, the scale isn't a ladder to climb. It's a mirror held up to the universe, asking not just how much energy we can use, but how wisely we can use it. The universe's explosive past and future. The story of the universe has always been written in light and fire. From the first seconds after the Big Bang to the quiet glow of galaxies today, energy has shaped everything. The Ophiuchus eruption is one chapter in a much older and ongoing tale. It wasn't the first cosmic detonation, and it won't be the last. Throughout the universe's history, similar outbursts have rewritten the structure of galaxies and sculpted the cosmic web. The early universe was far more chaotic than the calm, spiral-filled cosmos we see today. In those first few billion years, galaxies collided more frequently, black holes grew faster, and the density of matter was much higher. Violent eruptions were part of the universe's natural rhythm. Entire clusters were reshaped by these ancient tempests, which blasted out radiation powerful enough to sterilize any nearby worlds. The Ophiuchus event can be thought of as a modern echo of those primordial days. In a sense, it's a reminder that the universe still carries the memory of its turbulent youth. Even now, billions of years after the first stars burned bright, the same processes that once sculpted galaxies continue, only on a slower, grander scale. Astronomers have found evidence of fossil cavities, enormous empty bubbles left behind by previous explosions, suggesting that what we see in Ophiuchus today might have happened multiple times before. Each eruption leaves scars that take eons to fade, and the more scientists study them, the more they realize that the universe's calm appearance is deceptive. Beneath that serenity lies a long history of upheaval. Looking ahead, the future of the universe will likely be just as explosive. When the Milky Way eventually collides with the Andromeda Galaxy, an event expected to happen in about 4 billion years, the supermassive black holes at their centers will spiral toward one another. When they finally merge, the energy released in gravitational waves and radiation will dwarf anything humanity has ever imagined. Entire star systems will be thrown into new orbits, and for a brief cosmic moment, the night skies of both galaxies will blaze brighter than ever before. Even further into the future, when the universe grows colder and more diffuse, the nature of its explosions may change. There will be fewer stars forming, fewer galaxies colliding, and less gas for black holes to feed on. But that doesn't mean energy will stop flowing. Neutron stars, black holes, and the remnants of ancient galaxies will still interact, occasionally merging in bursts of gravitational energy. In a darkened universe, those rare outbursts will be like cosmic beacons, flashes of light against an ever-dimming background. Some researchers speculate that these giant eruptions could influence the expansion of the universe itself. On local scales, they redistribute matter and heat, changing the way galaxy clusters evolve. On grander scales, their collective energy may subtly affect how matter clumps together under gravity. While dark energy drives the universe's overall acceleration, these eruptions determine its texture. The difference between dense regions filled with galaxies and vast, empty voids stretching between them. Is there a rhythm to these outbursts? Could the universe itself operate on cycles far beyond human comprehension? Eons of build-up, followed by eruptions of unimaginable scale. Some theoretical physicists have wondered whether such cycles might repeat across cosmic epochs, with each wave of activity influencing the next. If true, Ophiuchus could be just one pulse in a series of universal heartbeats that have echoed since the dawn of time. If there's one lesson to take from the universe's explosive past, it's that creation is rarely gentle. Somewhere in the depths of time, countless Ophiuchus-like events have come and gone. The next great eruption could already be underway. The universe thrives on transformation. Even the most catastrophic events are part of a greater story, one still writing itself across the stars. Would you like to hear about more of these sorts of wild galactic-scale phenomena? Share your thoughts in the comments, and if you enjoyed the video, consider leaving a like and subscribing. Thanks for watching.